Welcome to the Sleepy Scientist. This is your quiet corner of the internet, a place to slow your thoughts, dim the noise of the day, and drift gently into curiosity. Tonight's journey takes us far below the waves, into a world where sunlight fades, pressure builds, and life has learned to thrive in the dark. We're exploring everything we know about the deep sea, the hidden half of our planet, where silence has shape and light is a living thing. Before we descend, I'd love to know, where in the world are you listening from tonight? The comments section has become a small constellation of time zones and night owls, and it's always wonderful to see where this calm corner of the internet reaches. If this kind of peaceful science helps you unwind, a gentle tap on the like button really does make a difference. And if you'd like to join our growing community of sleepy explorers, please subscribe, and to those who already have, thank you sincerely for being part of this slow, curious voyage. Don't forget to click the little notification bell so you won't miss the next quiet adventure waiting just over the horizon. And, well, I hope this video isn't too interesting and keeps you awake, but if it does, at least you'll fall asleep a little wiser. So take a deep breath, let the noise above fade away, and ask yourself, what really lies in the darkness, miles beneath the sea? The ocean covers more than 70% of Earth's surface, yet most of it remains unseen. As daylight dances across the shallows, only a thin layer of the sea ever feels the warmth of the sun. Beneath that bright skin lies a world colder, darker, and older than human history. A place more alien than Mars, but right beneath our feet. In this journey, you'll drift slowly through the layers of the ocean, from the soft blue of the surface to the black silence of the trenches. You'll feel the weight of pressure that would crush steel, see how life glows where no light reaches, and discover how chemistry, heat, and patience keep this hidden world alive. The deep sea isn't empty. It's a vast cathedral of motion, where creatures move like ghosts through a liquid night and mountains rise taller than any on land. We'll explore how energy finds its way without sunlight, how sound replaces sight, and how evolution sculpts life in slow motion. You'll meet the architects of this darkness, microbes, giants, and explorers, shaped by physics and time. This is the story of the deep, the planet's quiet heartbeat, the archive of its history, and perhaps its final frontier. So settle in, breathe slowly, and let the surface fade. Our descent begins where the light ends. Imagine standing on the shore at dusk, watching the last light of day ripple across the water. The surface glows silver blue for a moment before the waves swallow the colour. And that's where our story begins, at the thin, glittering edge of a world that stretches downward for nearly 11,000 meters. The ocean is layered like a sleeping giant's blanket, each fold deeper, colder and darker than the last. Scientists divide it into zones, not by strict walls, but by fading light and changing pressure. The uppermost layer, the epipelagic zone, is the ocean we know best. It reaches down about 200 meters, shallow enough for sunlight to feed the plankton, corals, and kelp forests that form the foundation of marine life. It's a place of movement and color, where most fish, turtles, and whales glide through beams of light that still remember the sky. But below that familiar shimmer lies a softer world, one that grows dim, then dark, and finally almost timeless. Just beneath the reach of the sun, the mesopelagic zone begins, sometimes called the twilight zone. It extends from about 200 to 1,000 meters deep. Here, blue light lingers the longest, scattering weakly through the water. Red, orange, and yellow vanish first, colors devoured by distance, until only ghostly shades of blue remain. This dim layer is cooler, quieter, and full of hidden travelers. Lanternfish drift in slow schools, their sides flickering with points of light like floating constellations. Transparent shrimp and jellyfish shimmer softly, and squid drift with eyes adapted to catch the faintest glimmer. Many of these creatures live by a simple rhythm. They rise toward the surface under cover of night to feed and sink back down before dawn. It's called diel vertical migration, and it's the largest daily movement of life on Earth. Billions of animals travelling up and down through the darkness, guided only by the faint pulse of light above. Keep descending, and the blue fades completely. At about 1,000 meters, we enter the bathypelagic zone, known as the midnight zone. No sunlight reaches this far. The water is near freezing, and the pressure is immense, more than 100 times what we feel at the surface. Yet even here, life continues. Creatures glow not by reflecting sunlight, but by creating their own. Bursts of bioluminescence that flash like Morse code across the abyss. It's a silent conversation of light. Warnings, lures, disguises, and invitations, all happening in total darkness. The air we breathe at sea level weighs lightly upon us, just 1 atmosphere of pressure. For every 10 meters you dive beneath the waves, another atmosphere is added, pressing in from all sides. At 1,000 meters, the weight above is 100 times what it is at the surface. Imagine the mass of a car pressing on every square inch of your body. And then imagine that life here has found a way not just to survive it, but to thrive. Deeper still lies the abyssopelagic zone, stretching from about 4,000 meters to 6,000 meters. The name abyss comes from a Greek word meaning bottomless, and it fits perfectly. Down here, temperatures hover just above freezing. Oxygen is scarce, and food arrives only as a slow, steady rain of tiny particles, the remains of life from above, drifting downward like snow. Scientists call it marine snow, a poetic name for the quiet fall of detritus that feeds everything below. It's easy to imagine this place as lifeless, yet the seabed is alive with worms, sea cucumbers, and starfish that crawl slowly across a landscape of endless silt. And finally, in the deepest trenches, from 6,000 meters to nearly 11,000 meters below the surface, we reach the Hadal zone, named for Hades, the underworld of Greek mythology. These narrow, plunging scars in the seafloor form where tectonic plates collide and one sinks beneath another. The Mariana Trench, for example, reaches almost 11,000 meters deep, where the pressure is more than 1,000 times that of the surface. Down there, a small submersible creaks and groans just from existing. Yet even here, life endures. Strange amphipods, snellfish, and microbial mats that cling to the edges of rocks where no sunlight has ever touched. Across all these layers, from the bright shallows to the blackest depths, the ocean carries a slow rhythm of change, temperature falling, oxygen thinning, and energy scattering like the last rays of twilight. There are no sharp borders, only gradients that melt into one another. The thermocline, for instance, is not a wall but a soft transition, a band of water where temperature drops rapidly with depth. Above it, currents mix and swirl, warmed by sunlight and wind. Below it, the water becomes still, heavy and ancient, its movements driven by slow global tides that take centuries to turn. To descend through these zones is to pass through time itself. Every 100 meters brings colder water formed decades ago. Every 1,000 meters brings layers untouched for centuries. The deep ocean is less like a place and more like a memory, vast, patient, and layered in silence. Scientists who study these regions often describe the experience as humbling. With each dive, they watch the familiar world disappear. First colour, then light, then any sense of scale. Shapes lose their meaning, replaced by shadows and motion. What begins as a dive into water becomes a journey into an entirely different reality. one defined by pressure, darkness, and the quiet persistence of life. If the surface of the sea is a reflection of the sky, then the deep is its opposite, a mirror of everything hidden and unknown. It reminds us that most of our planet exists beyond sight, that mystery isn't somewhere far away in space but right here below us. The next time you look out across the ocean, try to imagine that invisible world below. Kilometers of silence stretching down through blue and black, where gravity, light, and life play by rules that feel like poetry written in pressure and cold. Down there, the world is still turning softly, as if half asleep beneath its shimmering skin. The deeper you go, the heavier the world becomes. Every 10 meters beneath the surface, the weight of the ocean adds another full atmosphere of pressure, another layer of the sea pressing in from every direction. At the depth of an Olympic swimming pool, that extra pressure is already enough to make your ears pop. At 100 meters, it would crush a scuba tank flat. And at the bottom of the deepest trench, nearly 11,000 meters down, the pressure is more than 1,000 times what we feel here at the surface. It's the equivalent of balancing a stack of 50 jumbo jets on a single human body, and somehow life survives that. To understand how, it helps to start with what pressure really is. It isn't a thing in itself, but a relationship, a measure of how tightly molecules are packed together, how insistently they push against whatever's in their way. On land, we barely notice it. The atmosphere is a soft ocean of air, and our bodies have evolved to match it perfectly. But underwater, that balance shifts fast. The deeper we go, the more the molecules of water crowd together, forming a wall of force that squeezes anything with empty space inside it. Water, for all its fluid grace, is practically incompressible. You can push on it with incredible strength, and it barely changes at all. But air is very different. Light, elastic, full of room to move. That's why lungs, gas bladders, and even tiny air pockets inside bones become dangerous liabilities as the pressure builds. When an object containing gas descends, the volume of that gas shrinks in proportion to the pressure around it. Halve the volume, double the pressure. A simple balance, but one that defines the deep. A human body can only travel so far before this equation becomes impossible to bear. Divers who push beyond a few dozen meters need to breathe special gas mixtures and ascend carefully, giving their bodies time to readjust. But deep-sea animals never need to surface. They've solved the pressure problem in a dozen elegant ways. Many have no air spaces at all, no swim bladders, no hollow bones, nothing to collapse. Instead of lungs, fish at depth often rely on oil-filled bladders or jelly-like tissues that resist compression. Their bodies are made not of rigid materials that would snap under pressure, but of soft, flexible ones that simply yield and reshape. It's the same principle that lets a small balloon survive where a rigid submarine might crack. Flexibility is the secret currency of the deep. Some animals even have ribs that bend rather than break and skulls that are lightly reinforced, allowing them to adapt to the shifting pressure of their world. Others have evolved entirely different solutions. Deep-dwelling sharks fill their livers with low-density oils for buoyancy, while cephalopods rely on ammonia-filled tissues to maintain neutral buoyancy without needing air at all. At those depths, biology and physics blur together. Proteins, the molecular machines that make life possible, are sensitive to pressure too. Under extreme compression, their delicate shapes can warp, disrupting the chemical reactions they control. To compensate, deep-sea organisms tweak the chemistry of their cells. They produce special molecules called piezolites that stabilize proteins and membranes, preventing them from collapsing or sticking together. The result is a living system that can function flawlessly in a realm that would destroy almost every surface creature within seconds. Even at these crushing pressures, life remains astonishingly graceful. Consider the snailfish discovered in the Mariana Trench, a pale, delicate creature found at depths greater than 8,000 meters. It has no scales, no swim bladder, and no bones in the usual sense. Just soft cartilage and transparent flesh. It looks fragile enough to dissolve in sunlight, yet it thrives in conditions that would flatten a submarine. It's a quiet reminder that strength in the deep sea doesn't come from resisting pressure, but from becoming part of it. Where light fails, physics takes over in another way, through the quiet rain of darkness. Light cannot travel far through water. Every wavelength is absorbed at its own pace. Red first, then orange, then yellow. Only the faintest blue-green light makes it past a few hundred meters. Below 1,000 meters, even that vanishes completely. In that endless dark, evolution has played with the rules of vision, creating eyes that defy what we know about seeing. Some creatures grow enormous eyes, sensitive enough to detect the faint shimmer of bioluminescent flashes or the silhouette of a predator passing overhead. Others go in the opposite direction, abandoning sight altogether. In the deepest layers, eyes are often vestigial, small dark dots or even empty sockets. When there is no light to see, vision becomes a waste of energy. Instead, these animals invest in other senses, vibration, smell and pressure detection, reading the sea like a blind musician feeling the notes of a song. A few deep-sea fish even see the unseeable. Some have evolved photoreceptors tuned to wavelengths of blue-green light produced by other animals, effectively listening to the language of bioluminescence. Others have eyes split into two layers, one aimed upward to catch the faint glow from above, the other downward to detect their own reflections from below. A perfect countermeasure in a world where everything that glows is also a target. Darkness also shapes colour itself. Many deep-sea creatures are not black, as you might expect, but a deep translucent red. Because red light never reaches these depths, that colour is invisible. Red animals appear perfectly black to everything around them. It's a built-in cloak, a natural invisibility that requires no effort at all. In a realm ruled by scarcity, evolution is thrifty with its miracles. Humans, meanwhile, face their own struggle with pressure and darkness when exploring this world. Every deep-sea dive is a conversation with physics, an exercise in compromise between what's possible and what's safe. Submersibles must balance strength and weight, visibility and insulation. The deeper they go, the stronger the sphere that contains the crew must be. Engineers often use glass or titanium, materials that can withstand the crushing force, though even they have limits. One of the most iconic shapes in ocean exploration is the perfect sphere, not for beauty, but for physics. A sphere distributes pressure evenly across its surface, avoiding weak points that might collapse. Inside, explorers sit cocooned in a world of humming instruments, listening to the creaks of metal as the ocean presses in. To keep them safe, engineers fill the submersible with syntactic foam, a material made of countless microscopic glass spheres suspended in resin. It's strong, light, and capable of resisting immense pressure without crushing. In a poetic twist, the same principle that protects a snailfish's body, many small voids distributed evenly, also protects the machines that chase it into the abyss. It's humbling to realize that every journey into the deep, whether biological or mechanical, is a negotiation. Physics sets the rules, and life, or human ingenuity, finds the loopholes. Pressure squeezes, light fades, temperature drops, and still, something adapts. Every molecule of seawater becomes both an obstacle and a teacher. Down here, strength means softness. Sight means sensitivity. Motion means patience. The deep sea rewrites the rules we take for granted, showing that survival isn't about resisting the forces of nature, but understanding them. The deeper you go, the less the ocean feels like a body of water, and the more it feels like a living law, steady, silent and absolute. It doesn't roar or rage, it simply is, an invisible weight that shapes everything beneath it. and somehow in that still and endless pressure, life finds room to breathe. If pressure is the deep sea's weight, then cold is its heartbeat, steady, slow, and unchanging. Beneath the warm, restless skin of the ocean lies a realm where temperature barely moves. It sits between 1 and 4 degrees Celsius, cold enough to numb human skin within minutes, yet perfect for a kind of life that measures time not in days or seasons, but in centuries. The deep ocean's chill is more than a feeling. It's a physical rhythm, a metronome that sets the pace for everything that lives within it. Cold slows chemical reactions. It slows metabolism, growth, and decay. Down here, energy is precious, and every heartbeat, every twitch of a fin is an investment. A fish that might live for 10 years near the surface could live for 100 in the deep. Its pulse so slow, it feels almost suspended between moments. In this still cold, time stretches. Cells divide less often, enzymes turn more slowly, and creatures conserve energy by doing almost nothing at all. Some species live in a near state of pause, their lives stretched thin like the long notes of a song that never ends. This unhurried existence isn't a sign of weakness, it's a strategy. In the deep sea where food is scarce and change is rare, patience is the only way to survive. The chill of the deep is ancient, born from the slow breathing of the planet itself. Every drop of cold water down there once began as surface water somewhere near the poles. In the North Atlantic and around Antarctica, surface currents cool, grow saltier, and sink. These dense waters slide down continental shelves and spill into the abyss, forming a global loop known as thermohaline circulation. Thermo for temperature, haline for salt, is the planet's quiet conveyor belt, moving slowly but tirelessly, mixing the oceans and spreading heat around the globe. This underwater conveyor travels at a speed of just a few centimeters per second, but over time it becomes a planetary clock. A single parcel of water can take more than 1,000 years to complete its journey through the deep ocean and return to the surface. That means some of the water you see lapping against a beach today last saw daylight when Vikings were sailing the North Atlantic. It's a staggering thought. The ocean is a time machine, constantly recycling its memories through the pulse of cold and salt. Most of the deep ocean is uniformly cold, but not everywhere. There are eddies of slightly warmer water that drift like ghosts, remnants of surface currents pulled down by storms or by the chaotic mixing at continental slopes. These small temperature changes, often less than a single degree, can make the difference between life and death for deep-sea species. Many animals are finely tuned to their exact conditions. Even a subtle rise in temperature can push them beyond their narrow range of comfort. For the most part, though, the deep is unwaveringly stable. The seasons we know on land, winter, spring blooms, summer warmth, autumn decay, mean almost nothing here. Light never changes, temperature barely wavers, and storms above are felt only as distant pressure ripples. The deep ocean is one of the few places on Earth where time itself seems to stand still. That stillness has curious effects on the life. Cold water holds more oxygen than warm water, which gives deep-dwelling creatures a slow but steady supply of what they need to survive. But the same cold that preserves also limits. Chemical reactions are sluggish, and digestion, growth, and reproduction all happen at a glacial pace. Some deep-sea clams and corals are thought to live for hundreds, even thousands of years, adding just a fraction of a millimeter to their skeletons each year. Their lifespans are measured not in years, but in layers of calcium, tiny rings that mark centuries of stillness. Cold also shapes how creatures move. Muscles contract more slowly, nerves fire less frequently, and enzymes, those microscopic tools that make biology possible, struggle to work efficiently at low temperatures. To compensate, many deep-sea species produce cold-adapted enzymes, built with flexible structures that can keep turning even when heat is scarce. These enzymes are so efficient that scientists study them to improve industrial and medical processes on the surface. Nature, as it turns out, has already perfected the art of working slowly. Some animals take advantage of rare pockets of warmth, such as those near hydrothermal vents or volcanic ridges. These oases are like campfires in a frozen desert, brief flashes of heat that attract life from kilometers away. There, temperature gradients are sharp enough to be felt from one fin's length to the next. Move a few meters closer, and the water can go from icy to boiling. Move away again, and it's back to freezing stillness. These microclimates host some of the most diverse ecosystems on the planet, sustained not by sunlight, but by chemistry and heat leaking from the Earth's crust. But outside those rare oases, the deep sea's temperature is astonishingly constant. It acts as the Earth's great stabilizer, absorbing heat and slowing change. If the planet's surface climate is its mood, quick to flare and cool, then the deep ocean is its memory, recording slow shifts across centuries. When scientists measure deep-sea temperatures, they're reading the long history of climate itself, written one cold degree at a time. Cold is also the reason that the deep ocean preserves so much of the past. Shipwrecks, whale bones, even wooden artifacts can remain intact for hundreds of years, protected by the lack of oxygen, the absence of bacteria, and the freezing stability. The Titanic, resting nearly 4,000 meters down, is a perfect example. Slowly decaying but far more preserved than it would be in any warmer, shallower sea. In the deep, decay is simply too slow to keep up with time. Life here is patient because it must be. In the cold, every movement has a cost, and evolution has trimmed away anything wasteful. Some creatures feed only once every few months, storing energy until the next opportunity drifts by. Others have adapted antifreeze proteins to keep their cells from freezing solid. Even bacteria have learned to thrive at near-freezing temperatures, carrying on the slow work of recycling nutrients across the seafloor. For all its slowness, the cold doesn't make the deep sea lifeless, it makes it enduring. The steady chill allows life to spread evenly, to exist without hurry. The same cold that numbs and limits also protects. It shields fragile creatures from sudden changes, keeps ancient lineages alive, and ensures that the deep sea remains one of the most stable environments on Earth. When you imagine the deep ocean, think not of a place frozen in time, but of one moving to a slower rhythm, a world where the pulse of heat and cold keeps everything in balance, where even the smallest shift of a degree is a conversation between continents. Down there, the ocean doesn't rush. It waits, listens, and carries the memory of the planet's oldest breath, circulating quietly through the dark, reminding us that sometimes the slowest heartbeat lasts the longest. In the deep ocean, where sunlight fades into memory, light takes on a new meaning. It is no longer borrowed from the sun or reflected from the surface, it is made from within. Here, light is alive. It flickers from fish, glows from jellyfish, and drips like blue fire from drifting plankton. This is bioluminescence, the quiet art of making light out of darkness, and it is one of nature's most hauntingly beautiful inventions. At its heart, bioluminescence is chemistry, not magic. It happens when a molecule called luciferin reacts with oxygen in the presence of an enzyme named luciferase. The reaction releases energy not as heat, but as a soft glow of visible light. It's the same process that makes fireflies shimmer on warm summer nights. But underwater, it plays out on a far grander stage. In the ocean, this reaction happens across millions of species, from microscopic plankton to colossal squid, turning the darkness into a living galaxy of blue and green. Most of the light we see in the deep is blue, and there's a simple reason for that. Blue wavelengths travel farthest through water, while reds and yellows are swallowed almost immediately. In a world where sunlight has vanished, blue is the only colour that can truly move, the universal language of the abyss. and for creatures that live there, this light is everything: defense, disguise, lure, and communication all rolled into one. One of the most surprising uses of bioluminescence is camouflage. It sounds strange. How can glowing help you hide? But many animals that live in the midwater zone face a unique problem. Predators below them look upward, scanning for silhouettes against the faint glow from above. To vanish, these animals produce their own soft light on their bellies, matching the brightness and colour of the distant surface. This trick, known as counter-illumination, erases their shadows and makes them nearly invisible. Some squid even adjust their glow in real time, dimming or brightening to match the shifting light above, the deep-sea version of stealth technology. For others, bioluminescence is a lure, a quiet trap in the dark. The most famous of these hunters is the anglerfish, a creature whose strange beauty lies in its patience. From the top of its head grows a small rod tipped with a glowing bulb, a biological fishing line. In the darkness, that light sways and flickers like a tiny drifting meal. Curious prey swim closer, and when they do, the anglerfish opens its enormous mouth in a flash and swallows them whole. The lure is powered by a symbiotic bacteria that live inside it, tiny partners that trade light for safety. But not every glow is meant for hunting. Some are desperate signals of survival. When threatened, certain shrimp release glowing clouds, a kind of defensive smoke screen made of light. The sudden flash confuses predators, buying just enough time to escape. Jellyfish, too, have their luminous defenses. The Atolla jellyfish, for instance, creates a pulsing blue ring when attacked, a glowing alarm meant to attract even larger hunters that might chase off its attacker. In the deep sea, sometimes the best way to survive is to shout your danger in light. Other displays are subtler, almost conversational. Many species use flashes and patterns as a kind of silent Morse code. Some deep-sea fish communicate through rhythmic blinks, signalling territory, courtship, or recognition. A species of lanternfish might have a pattern so unique that its glow is as distinct as a fingerprint. Even plankton, the microscopic drifters that fill the upper layers of the sea, join in. When disturbed, they release waves of light that ripple through the water, like an underwater aurora. Sailors of old called this phenomenon the sea on fire, watching in awe as ships cut glowing trails through the night. To see this light is to glimpse something ancient. Bioluminescence likely evolved more than 40 separate times in the history of life, an astonishing case of nature solving the same problem in many different ways. In the deep ocean, it's estimated that more than 80% of organisms are capable of producing light. In other words, darkness itself has become the exception. The forms it takes are endless. Some creatures emit steady glows, others pulse in rhythmic bursts, and some release light in cascading curtains that drift away like smoke. The vampire squid, despite its eerie name, is one of the most graceful performers. When startled, it turns its body inside out, revealing glowing blue spots along its arms, tiny pinpoints that flash and fade like stars. The display disorients predators, but to us it looks almost like art. Another master of light is the cookie-cutter shark, a small predator with a glowing underbelly that disguises its shape. It swims unseen beneath large animals, then darts upwards to bite out perfect circular chunks of flesh, leaving behind the neat scars that gave it its name. It's a reminder that in the deep sea, even beauty can bite. And then there's the stoplight loose jaw, a fish with a remarkable talent. It produces two colours of light, red and blue. Red light doesn't travel far underwater, so to most creatures, it's invisible. But the loose jaw can see its own red beam, giving it a private flashlight that lets it spot prey without being seen. It's stealth by colour, evolution's quiet wink to physics. Every display of bioluminescence tells a story written in flashes and glow, It's a form of communication that doesn't rely on sound or movement, perfect for a world where visibility is near zero and silence is constant. It allows creatures to coordinate, to find each other, to warn or deceive, and to express life in the one medium still available: light. Even on a planetary scale, this living light connects us. Astronauts aboard the International Space Station have occasionally seen faint glows in the ocean at night. Vast patches of luminescent plankton stretching for hundreds of kilometers, turning the sea into a shimmering canvas. For a few fleeting hours, the Earth itself seems to glow from within. What's perhaps most beautiful about bioluminescence is its restraint. The light is never harsh or blinding, it flickers softly, hums quietly, and vanishes as suddenly as it appears. It's the language of a world that has learned to speak gently. No wasted energy, no unnecessary brightness, just the faint glow of survival, communication, and mystery. Scientists still don't know every secret behind this phenomenon. New glowing species are discovered almost every year, from deep-sea corals to planktonic worms and even sharks. Each one adds a new accent to the ocean's silent conversation. And as our instruments improve, we continue to find that the dark is not as empty as it seems. It's alive with whispers of light. So when you think of the deep sea, don't picture it as black and lifeless. Imagine instead a slow drifting ballet of light, threads of blue weaving through the dark, creatures blinking like distant stars, and whole mountainsides glowing in soft patterns of motion. Down there, light is not something to chase or fear. It's the way life remembers itself, a quiet signal that even in absolute darkness, something still shines. Every living thing on the surface of our planet owes its energy to the sun. From the smallest blade of grass to the largest blue whale, nearly every heartbeat, every movement, every breath is powered by light that fell from the sky. But deep beneath the ocean, where sunlight cannot reach, life has written its own rulebook. Here, existence is not powered by the sky above, but by the earth below. This is the realm of chemosynthesis, the art of living without sunlight. Instead of drawing energy from photons, chemosynthetic organisms pull it from the chemistry of the planet itself, from the quiet exchange of molecules that seep out of rocks and vents at the bottom of the sea. They are the unseen chemists of the abyss, the first link in a food chain that has never seen daylight. The idea of life without the sun once seemed impossible. For centuries, scientists assumed that photosynthesis, the process by which plants and algae convert light into energy, was the foundation of all ecosystems. But in the late 20th century, a series of deep-sea expeditions changed that view forever. When scientists first explored the ocean floor near hydrothermal vents, they discovered entire communities thriving in complete darkness. Tube worms, crabs and fish swarmed around cracks in the Earth's crust where superheated water gushed out, rich in minerals and chemicals. There, amid scalding heat and toxic plumes, life was flourishing without a single ray of light. At the heart of these ecosystems are the chemosynthetic microbes, the planet's smallest and arguably most important engineers. These microscopic organisms live inside rocks, sediments, and the tissues of larger animals. They make energy by oxidizing compounds like hydrogen sulfide, methane or ammonia, chemicals that seep out from beneath the sea floor. Where photosynthesis uses carbon dioxide and sunlight to make sugars, chemosynthesis swaps out sunlight for chemical reactions. Is it a bit like running an engine on fumes rather than fuel, slow, efficient, and entirely self-contained? A simple example comes from the bacteria living near hydrothermal vents. The vents release water that's not only hot, but loaded with hydrogen sulfide, a compound that would be lethal to most life. These bacteria take that chemical and strip it of its energy, combining it with carbon dioxide to form organic matter, the basis of food. The reaction looks something like this. Carbon dioxide plus hydrogen sulfide yields sugar and sulfur. The byproduct might be unpleasant, but the result is pure sustenance. This chemical alchemy forms the backbone of entire deep-sea ecosystems. Giant tube worms, some more than 2 meters long, host colonies of these bacteria within their bodies. The worms themselves have no mouths, no stomachs, and no digestive systems. They rely completely on their microbial partners to produce nutrients from the vent water flowing around them. In return, the worms supply the bacteria with the raw materials they need: oxygen, carbon dioxide, and hydrogen sulfide, drawn in through specialized plumes. It's a perfect partnership, born of chemistry and patience. Around them, crabs, clams, shrimp, and fish feed on the microbial mats that coat the rocks, or on each other, weaving a web of life entirely detached from sunlight. It's as if an entire ecosystem has sprouted from stone, a living oasis built on the breath of the earth itself. Chemosynthesis is not limited to the violent heat of hydrothermal vents. It happens in cooler, quieter places too, along cold seeps, where methane and hydrogen sulfide leak slowly from the seabed. There, the chemistry is gentler. But the principle is the same. Microbes tap into these energy sources, forming the base of food webs that stretch upward through worms, crustaceans, and fish. These seeps are often covered in colonies of mussels and clams that, like the tube worms, host symbiotic bacteria within their tissues. To the casual eye, it looks like a meadow of shells. To science, it's an entire world powered by chemistry. To understand just how remarkable this is, it helps to compare it with life at the surface. Photosynthetic ecosystems, the forests, grasslands, and coral reefs, are powered by a flood of energy. Every square meter of sunlight brings hundreds of watts of potential power, enough to drive fast metabolisms, rapid growth, and dazzling diversity. But chemosynthetic ecosystems live on a trickle. The energy released by chemical reactions at vents and seeps is millions of times weaker than the flood of solar energy falling on the surface. And yet, that trickle is enough. In a world where life moves slowly, energy doesn't need to arrive fast. It just needs to be steady. Chemosynthetic microbes don't chase abundancy, they rely on constancy. A vent might last a few decades before closing. A seep might persist for centuries, but as long as the chemistry continues, so does life. It's the biological equivalent of surviving on a single candle flame instead of a roaring fire, patient, efficient, and enduring. What's fascinating is that these deep ecosystems blur the line between biology and geology. They exist exactly where the planet's internal heat meets its outer ocean, at the seams where tectonic plates spread or collide. The energy comes not from above, but from within, from the radioactive decay of minerals, from the friction of moving plates, and from the slow exhalation of gases trapped since the Earth first formed. These places remind us that life is not simply a passenger on the planet's surface, it's woven into the planet's chemistry itself. Some scientists think that life may have started in such places. Long before sunlight reached the surface through a stable atmosphere, the early Earth was covered in volcanic oceans rich in minerals and gases. Hydrothermal vents would have provided just the right condition: warm water, chemical gradients, and protective mineral surfaces for the first reactions that led to life. Even today, the microbes that thrive around vents seem like living fossils, carrying echoes of those ancient beginnings. The discovery of chemosynthesis didn't just rewrite our understanding of Earth, it expanded our imagination for what life might look like elsewhere. If living systems can exist in complete darkness, powered only by chemical energy, then perhaps other worlds, icy moons like Europa or Enceladus, might also harbour life beneath their frozen shells. Each time a spacecraft detects plumes of water or traces of methane rising from those moons, scientists are reminded of our own planet's hidden ecosystems deep below. Chemosynthesis proves that life doesn't need a perfect world, it doesn't need sunlight or warmth or easy energy. It just needs balance, a gradient, a place where two forces meet and exchange possibilities. The microbes that build their lives on chemical whispers show us that energy is everywhere, waiting to be captured by whatever form of life is clever enough to use it. In the grand story of the planet, chemosynthesis is both humble and profound. It's quiet, almost invisible, yet it supports entire worlds that would otherwise be barren. It teaches that even when the lights go out, the machinery of life can keep turning, powered not by the heavens, but by the deep pulse of the earth itself. So while sunlight may rule the surface, the deep reminds us that life's true genius lies in its adaptability. Whether in warmth or cold, light or darkness, abundance or scarcity, life always finds a way to turn the impossible into the ordinary. In the deep ocean, it has done so with elegance, feeding on stone, breathing in chemistry, and glowing faintly in the endless night. The deep sea is a realm of extremes, where life has been sculpted into shapes that defy easy explanation. Some creatures down there grow to astonishing sizes: giant squid, enormous amphipods, jellyfish with tentacles longer than blue whales. Others shrink to almost nothing, tiny translucent dots adrift in an endless void. It is a place where both gigantism and miniaturization thrive side by side, each shaped by the same simple forces: darkness, pressure, scarcity, and time. Deep-sea gigantism is one of nature's most mysterious patterns. At depths where food is rare and temperatures are cold, many species grow to sizes far greater than their shallow water relatives. The giant isopod, for instance, is a cousin of the common woodlouse found under garden stones. While its land-dwelling relatives barely reach a few centimetres, the deep-sea version can grow half a metre long, a living dinner plate with legs. Likewise, amphipods that in surface waters would be no larger than a grain of rice can reach the length of a human hand in the abyss. Why such size? One theory links it to metabolic efficiency. In the cold, chemical reactions slow down and larger bodies lose heat more slowly, making them more energy efficient. Bigger animals can store more energy, travel farther in search of food, and survive longer between meals. In an environment where dinner might drift by once a month, endurance is everything. Pressure also plays a role. At great depths, water presses in from all sides with immense force, and having a larger body helps distribute that pressure more evenly. But perhaps the simplest reason for gigantism is patience. Many deep-sea species grow incredibly slowly, taking decades to reach maturity. With no need to rush, evolution has favoured size over speed, large bodies built not for quick survival, but for long, steady persistence. At the same time, the deep sea is home to some of the smallest, most fragile creatures on Earth. Transparency is their defense. When there's no place to hide, invisibility is the best strategy. Countless jellyfish, larvae, and planktonic drifters have evolved to be almost completely clear, their bodies little more than a whisper of living gel. Light passes through them, and predators glide past none the wiser. These ghost-like beings are often made mostly of wood, up to 95% in some cases. Their tissues are soft, gelatinous, and flexible, which helps them withstand the pressure of the deep without being crushed. Bone and muscle would only weigh them down. Softness paradoxically becomes strength. The result is an ocean filled with creatures that move like drifting thoughts, slow, fluid, and silent. In the upper layers of the sea, animals must burn energy constantly just to stay afloat. But in the abyss, energy conservation is an art form. Many deep-sea creatures have found ways to achieve perfect neutral buoyancy, where their weight and the water around them are in perfect balance. Some fill their bodies with oils that are lighter than water. Others use compounds like ammonium chloride, the same chemical found in household cleaners, to reduce their density. It doesn't sound elegant, but it works. A squid filled with just the right amount of ammonia solution can hover motionless for hours without using a single flick of muscle. Skeletons, too, become optional in a world without the pull of gravity. Many deep-sea fish have thin, underdeveloped bones and muscles. Their bodies are flabby, their flesh gelatinous. On the surface, these features would make them clumsy and vulnerable, but in the deep they're ideal. There's no need for speed or strength when both prey and predator drift slowly. When scientists bring these animals to the surface, the sudden drop in pressure leaves them looking deflated or distorted. Fragile beings built for a world of weight, undone when that weight is gone. The appearance of deep-sea creatures often blurs the line between the beautiful and the bizarre. The giant squid, for example, is a symbol of both extremes, a colossal animal with the soft anatomy of a jellyfish and the nervous precision of a predator. It can reach lengths of over 12 meters, yet its body is almost entirely muscle and water. For centuries, sailors told stories of monsters rising from the depths, but the truth is even more fascinating. These creatures are living lessons in physics and patience, designed by pressure and perfected by time. Other species take the opposite route, shrinking down to microscopic scales to survive. In the sediments of the abyss live countless tiny worms, crustaceans and microbes that make up what scientists call the meiofauna, the small life between the grains. These miniature creatures live slow, cautious lives, feeding on detritus and organic films. They move through the sand like living dust motes, their world measured in millimeters, their lifespans stretching quietly for years. At both ends of the size spectrum, life follows the same rule: do more with less. In the deep, energy is a luxury, and evolution rewards those who can stretch it the farthest. Giants store it. Ghosts avoid spending it. Every adaptation, from oil-filled livers to transparent skin, is part of a long negotiation between hunger, physics, and time. The transparency of many deep-sea creatures is not only camouflage, but also economy. Pigments require energy to produce, and in a place where every molecule of energy counts, colour is a waste. Why build a pattern no one will see? Many deep-sea fish and invertebrates have simply stopped making pigment altogether. Their bodies are clear, their organs faintly outlined, and their eyes, if they have them, are often the only visible feature. Even light organs, though beautiful, serve practical purposes. Some species glow faintly to attract prey, to communicate, or to match the ambient light from above. Others use small patches of bioluminescence to hide their outlines. There's elegance in the way every adaptation in the deep is dual purpose, beauty and function fused into one. Because resources are scarce, most deep-sea creatures grow slowly and live long. They take years, sometimes decades, to reach adulthood. Reproduction is infrequent, but when it happens, it's strategic. Large, energy-rich eggs or larvae that drift with the currents until they find a home. This evolutionary patience gives the deep sea its peculiar stillness. Life here is not in a hurry. It doesn't chase or compete the way it does near the surface. Instead, it persists, methodically, carefully, generation after generation. Some of the oldest living animals known to science come from these depths. Deep-sea corals can live for thousands of years. Their growth so slow, it can only be measured under a microscope. The Greenland shark, a creature of the cold and dark North Atlantic, grows at less than 1 centimeter a year and may live for over 400 years. These are not creatures built for speed or spectacle, but for duration. Quiet lives unfolding over vast spans of time. Taken together, the giants and ghosts of the deep remind us that there's no single formula for survival. Nature solves the same problem in 100 ways: grow larger, grow smaller, turn transparent, grow patient. Each solution is a response to the same conditions: darkness, scarcity, and the immense stillness of water that never sees the sun. In the end, the deep ocean isn't filled with monsters or miracles. It's filled with experiments, slow, beautiful compromises between physics and life. Every shape, every size, every soft outline drifting through the black water is a testament to the fact that even under crushing pressure, life refuses to stay still. It grows large, it grows small, it fades, it shines, always finding a way to belong to the dark. Down in the deep, where light fades away, sound becomes the language of the sea. It carries messages, maps, and even moods, echoing across distances that light could never hope to reach. In water, sound travels about 4 times faster than in air and can move for hundreds, even thousands of kilometers without fading. Where sight ends, hearing begins, and for many creatures, sound is not just a sense, but a way of seeing. The reason is simple physics. Water is denser than air, so its molecules are packed more tightly together. When something vibrates, a whale's call, a snapping shrimp, a distant storm, those vibrations pass efficiently from one molecule to the next. The result is a medium that conducts sound with remarkable clarity. In the open ocean, a single low-frequency note can circle an entire basin, bouncing between layers of warm and cold water like a voice whispering through a labyrinth. In the vast acoustic world, vision becomes almost irrelevant. Many deep-sea creatures are blind or nearly so, but the sensitivity to vibration is extraordinary. Some fish can detect minute changes in pressure through lines of tiny sensory pores along their bodies. Others use specialized organs to pick up sound waves or the faint tremors of movement in the water. Even a single drop of sand settling on the seafloor can be heard by the right listener. For large marine mammals, sound is more than communication. It's navigation. Whales and dolphins use echolocation, a biological sonar that turns the ocean into an echoing map. They emit short bursts of sound and listen for the returning echoes, reading them with astonishing precision. Each click reveals the shape, distance, and even texture of objects nearby. A dolphin can detect a small fish from dozens of meters away, and a sperm whale can see a giant squid through pitch-black water at depths where sunlight has been absent for millions of years. Imagine living in such a world, one where everything around you exists not as colour and light, but as texture and rhythm. Sound paints the landscape, defining coral towers, drifting shoals, and even the open void between them. Every pulse, pop and hum is part of a 3-dimensional soundscape that changes by the hour. The ocean's natural symphony is surprisingly rich. At the surface, wind and waves create a constant hush, a white noise that fades only in the stillest weather. Rain adds a soft patter. Distant storms contribute long, low rumbles that roll across entire seas. In polar waters, the cracking of ice fills the depths with sharp explosive notes, an underwater percussion created by the planet's frozen breath. Life, too, is never silent. Coral reefs are alive with clicks, snaps and grunts, the chatter of shrimp, fish and mollusks all communicating or hunting in their own frequencies. Some fish call to one another by vibrating their swim bladders, producing deep drum-like sounds. Others grind their teeth, hum or croak. To us, it might sound chaotic, but to an animal tuned to this sonic world, it's a dense network of information, a living radio spectrum that never sleeps. In the deep sea, these sounds stretch and change. High-frequency noises fade quickly, leaving behind only the low resonant tones that can travel across entire oceans. The sound of a distant earthquake might pass beneath the same waters where a blue whale sings, the two events overlapping across time and distance. Researchers have recorded whale calls travelling from one side of the Pacific Ocean to the other, a journey of thousands of kilometres. It's humbling to think that a whale's song could pass unnoticed beneath the feet of sailors halfway around the world. Humans have learned to listen too. Because light cannot penetrate far underwater, scientists see the deep using sound. Sonar, short for sound navigation and ranging, sends out pulses that bounce off of objects and return as echoes. The time delay reveals distance, the shape of the echo reveals form. With this simple principle, ships can map the seafloor, locate schools of fish, and even detect underwater volcanoes. It's how we've discovered much of what we know about the ocean's hidden topography. Its canyons, ridges, and plains. There are different kinds of sonar. Active sonar sends out a ping and listens for the echo, while passive sonar simply listens. The latter is less intrusive, used to study natural sounds rather than create them. With these tools, scientists can eavesdrop on whales, track migrations, and monitor the creaking of shifting ice shelves or the slow settling of sediments. The ocean is full of subtle voices, and we're only beginning to understand what they're saying. Yet, as with most human inventions, our listening comes with unintended noise. The engines of ships, seismic surveys, and military sonar have added new layers of sound to the sea, ones that marine life never evolved to handle. Low-frequency noise from cargo vessels can drown out whale songs across vast distances. Explosive pulses used for oil exploration can disrupt delicate communication networks among dolphins and fish. Even a single loud sonar blast can cause panic in animals that rely on echoes to navigate, leading them to beach themselves in confusion. Scientists and engineers are working to make the ocean a quieter place again, to develop technologies that reduce this artificial sound. Quieter propellers, slower shipping routes, and passive mapping methods are all helping to give the ocean back its voice. Because for creatures that live by sound, silence isn't emptiness, it's safety. The idea of an underwater soundscape might feel abstract, but it's as real as the forests we walk through or the skies we fly under. It's an environment built from vibration and echo, where direction is felt rather than seen. Whales may navigate by tracing familiar acoustic landmarks, the way sound bounces off seamounts or the echo patterns of continental slopes. For them, each stretch of ocean has a unique acoustic fingerprint, like a melody they can follow year after year. Picture it this way. The deep ocean is like a vast cathedral, built not of stone but of water. Every sound, from the slow groan of shifting plates to the faint rustle of a passing squid, reverberates through its chambers. Some echoes return in seconds, others take hours. To the beings who live there, this echoing world is a map, a memory, and a form of communication all at once. If you could listen to it, really listen, you'd hear layers of sound stacked like clouds, the faint hiss of sand sliding down a slope, the distant beat of whale heartbeats echoing through the thermocline, and the deep, slow breathing of the sea itself. In that space, silence isn't the absence of sound, it's the moment between them, the pause before another echo begins. The ocean speaks constantly, but not loudly. It hums, sighs, and whispers, turning pressure into poetry. Every creature that calls, clicks, or listens adds a note to the composition. Together they create a planet-sized symphony, one that stretches from the crashing waves at the surface to the quietest trenches below, reminding us that in the deep, sound is not just how life survives, but how it feels its way through the dark. Far below the reach of light and weather, the ocean floor stretches out into an almost endless plain, a world so vast that it covers more than half of Earth's entire surface. The abyssal plains are the planet's largest habitat, yet they remain among its least explored. They are the flatlands of the deep sea, vast fields of soft sediment stretching between underwater mountains and trenches where time moves at the pace of falling dust. If you could stand there, which of course you cannot, the view would be both simple and surreal. The seafloor lies as smooth as an ancient desert, rippled only by the faint traces of currents or the slow slide of silt. The water above you would be a column nearly 4,000 meters thick, pressing down with quiet weight. No wind, no waves, no sunlight. Just the dim blue-black hush of eternity. This is a world built not from abundance but from scarcity. The abyssal plains are fed by a gentle rain of particles drifting down from the surface, the marine snow. Every speck of this snow is a tiny relic. Fragments of dead plankton, pieces of shells, scales, and dust. Individually they are nothing, but together they sustain the deep. It can take weeks or even months for these particles to fall from the sunlit layer to the seafloor. By the time they arrive, they are fragile ghosts of what they once were, faint traces of life feeding a world that has learned to survive on almost nothing. Because food is scarce, everything that lives here moves slowly, carefully, and with purpose. Worms, sea cucumbers, brittle stars, and crustaceans sift the sediment, harvesting whatever nutrients they can find. Scavengers like grenadiers and sea spiders drift through the gloom, following invisible trails of scent that lead them to a fallen fish or a piece of drifting carrion. When something large like a whale falls to the bottom, becomes a festival, a sudden brief explosion of life. Within hours, crabs, hagfish, and amphipods gather in the darkness, stripping the carcass clean. After they are gone, smaller creatures move in to feast on what remains, and finally bacteria take over, breaking down the last traces into minerals that return to the sediment. Nothing is wasted, everything is used. This slow recycling gives the abyssal plain a stillness that is more than quiet, it's patient. Here, evolution has learned restraint. Creatures live long lives, growing slowly, conserving energy. Some deep-sea corals on these plains may be older than the pyramids, each ring of growth marking another century of calm. Despite its apparent emptiness, the abyss is full of subtle motion. The seafloor is alive with bioturbation, the endless rearranging of sediment by the creatures that live within it. Tiny worms and burrowing sea cucumbers tunnel through the mud, leaving behind winding trails and small mounds. Each movement mixes the sediment, aerating it, and helping nutrients spread. It's like the slow breathing of the planet, invisible but vital. These quiet diggers shape the chemistry of the seabed, in the same way that roots and insects shape the soil of a forest. To the human eye, there is little colour here. The lightless water filters out every hue except the faintest grey-blue, and most animals are white, red, or transparent. But there is beauty in the textures, ripples carved by sluggish currents, trails etched by wandering snails, delicate filigrees left by worms. The plain is covered in fine patterns that look like the brushstrokes of a careful artist. Even shadows move slowly, diffused through kilometres of dark water until they blur into the same soft tone. Occasionally the monotony breaks. Underwater volcanoes rise from the plain like solitary mountains. Some are covered in layers of manganese nodules, small metallic spheres that form around tiny fragments of debris over millions of years. These nodules grow so slowly that each one is a time capsule, recording chemical traces of the ancient ocean. Around them, deep-sea sponges and corals anchor themselves, catching what little organic material drifts by. To a passing submersible's lights, the scene looks almost lunar, a dusty alien landscape scattered with the slow architecture of life. The animals of this world have evolved remarkable ways to cope with its austerity. Many have gelatinous bodies that require little energy to build or maintain. Others have extremely slow metabolisms, allowing them to survive long stretches without food. Some species can go years between meals, waiting for the next pulse of organic matter from above. In a way, the abyss is an economy of patience. Every movement, every breath, every heartbeat calculated to stretch energy as far as possible. Fish here often have long, slender bodies and small eyes. There is no need for vision when darkness never ends. Instead, they rely on smell and vibration, using fine sensory hairs to detect faint water movements caused by prey or predators. The grenadier, one of the most common deep-sea fish, embodies this design. It glides slowly above the sediment, tail twitching in measured beats, its large head and sensitive barbels sweeping the mud like a living radar. Even in its stillness, the abyssal plain plays a crucial role in Earth's systems. It acts as a carbon sink, storing organic material that settles from the upper ocean. Over time, this carbon becomes buried in sediment, locking away greenhouse gases and helping regulate the planet's climate. Each year, trillions of tiny particles drift down, settle, and are sealed by the next layer of silt. It is a silent service, carried out endlessly by gravity and time. But for all its apparent calm, the abyss is not entirely unchanging. Earthquakes, landslides, and shifting currents can disturb the seafloor, sending clouds of sediment billowing upward like underwater dust storms. These events are rare but powerful, reshaping entire regions and redistributing nutrients. In some places, slow-moving turbidity currents, underwater rivers of dense sediment, carve deep channels through the plains, creating canyons and valleys invisible from above. The abyssal plains also remind us how little of the planet we've truly seen. Less than a quarter of the global seafloor has been mapped in detail, and much of what we know comes from brief glimpses, a few hours of footage, a few samples collected by robotic arms. For all our technology, this is still one of the most mysterious landscapes on Earth. And yet, despite its emptiness, there's a strange comfort in the abyss. It's a place untouched by noise or haste, where life endures quietly, sustained by particles no larger than dust. It's the ocean's long exhale, the place where everything that once lived eventually comes to rest. The surface world rushes, burns, and rebuilds, but down here, time has no urgency. If the coral reef is the ocean's bustling city, then the abyssal plain is its open desert, vast, silent, and beautiful in its restraint. Every ripple in the sediment, every drifting fragment of marine snow, tells a story of patience and persistence. Even in the loneliest depths, life continues its steady rhythm, reminding us that beauty doesn't always shout. Sometimes it whispers softly across the quietest plains on Earth. Imagine descending past the last of the abyssal plains, where the seafloor suddenly drops away beneath you. The landscape that once seemed endless now folds into itself, curving downward into a chasm. This is the beginning of the Hadal realm, the deepest environment on Earth, found in the oceanic trenches where tectonic plates collide. Here, the planet quite literally swallows itself. These trenches are not small cracks, they are immense scars that run for thousands of kilometers across the ocean floor. The Mariana Trench, the deepest of them all, plunges nearly 11,000 meters beneath the surface, deeper than Mount Everest is tall. Others, like the Tonga-Kuril-Kamchatka and Philippine trenches, reach nearly as far. To look at a map of the ocean floor is to see them as dark blue ribbons along the edges of continents, marking where one slab of Earth slides beneath another. This process, called subduction, is part of the planet's slow tectonic heartbeat. Oceanic crust, heavy with minerals and cooled by age, is pulled downward into the mantle while new crust forms at mid-ocean ridges. The trenches are the downward half of that cycle, where the planet recycles itself, grain by grain, over millions of years. Along these boundaries, heat and pressure create earthquakes, volcanoes, and deep-sea landscapes unlike anywhere else. The geometry of a trench is striking. Imagine a long narrow valley, steep-walled and curved like the blade of a crescent moon. The upper slope drops sharply, then levels out into the Hadal zone. Depths from 6,000 to nearly 11,000 meters. At the very bottom lies the Hadal floor, a ribbon of sediment and rock just a few kilometers wide but stretching for hundreds of kilometers. It's the most remote habitat on the planet, cut off from sunlight, tides, and almost every influence of the surface world. The pressure here is beyond comprehension. For every 10 meters of depth, another atmosphere of pressure is added. At 11,000 meters, that's more than 1,000 times the pressure we feel at sea level, enough to crush most materials and collapse air-filled spaces instantly. A styrofoam cup lowered to this depth returns the size of a thimble. Yet life somehow not only endures but thrives. Creatures of the Hadal zone are built from softness. Their bodies have no air pockets to crush, no rigid bones to snap. Their cells are filled with flexible membranes and fluids that balance the pressure around them perfectly. Deep-sea fish like the Mariana snailfish are ghostly and delicate, with translucent skin and bodies that seem almost unfinished. They live where no other vertebrate can survive, gliding effortlessly through a world that would destroy anything less perfectly adapted. The secret lies in chemistry. Under immense pressure, proteins, the microscopic machines that make life work, tend to deform and lose their shape. To counter this, Hadal organisms produce special molecules called piezolites, which help stabilize these proteins and keep them functioning. These compounds, often derived from simple amino acids, act like internal armor at the molecular level, ensuring that biological reactions continue smoothly even under crushing force. Pressure also changes the rules of physics in surprising ways. Water molecules are squeezed closer together, altering their properties. Even sound behaves differently, traveling faster and bending along temperature and pressure gradients. For humans, these effects make exploration difficult. Instruments malfunction, electronics short-circuit, and metal bends where it should not. For life, though, it's simply the background hum of existence. Evolution has had millions of years to perfect its responses to the deep. The isolation of these trenches gives them an almost mythical quality. Each one is like a biological island, separated from others by vast ridges and plains. Scientists call this pattern-taken Hadal endemism, the idea that each Dahimij trench harbours its own unique species found nowhere else on Earth. The animals that evolve here are cut off from the rest of the ocean by depth and geography, adapting specifically to their own trench's chemistry, temperature and pressure. One amphipod might live in the Mariana Trench but not in the Tonga. One type of snailfish may flourish in the Kermadec but nowhere else. This isolation has turned the trenches into natural laboratories of evolution. In their silence, they've created worlds within worlds, deep valleys that operate on their own timescales. The species here are ancient and often fragile, adapted to perfect stability. Even a small change, such as warmer water or altered oxygen levels from above, can ripple down and upset the balance. To descend into a trench is to experience the ocean's final transformation. As you pass 6,000 meters, the last traces of abyssal life fade. The water grows denser, the darkness thicker, and the sense of space changes. There is no horizon here, only a slow narrowing of the world into shadow. The sediment at the bottom is fine and soft like grey powder. Every step or movement sends a cloud drifting upward, where it hangs suspended for hours. The sounds are minimal, a faint hum from the instruments, the creak of pressure against the hull, and the occasional soft ping of sonar reflecting off unseen walls. In that distance, even a single movement feels monumental. The trench walls rise steeply on either side, covered in loose sediment and small rocks that tumble slowly downward. Occasionally, a creature moves through the camera's light. A shrimp-like amphipod, a pale snailfish, or a cluster of transparent sea cucumbers that look like drifting leaves. At these depths, light from the submersible is the first illumination this landscape has ever known. There are no shadows because there is no light to cast them, only the gentle diffusion of beams through suspended particles. It feels less like entering a space and more like entering time itself. A slow, cold eternity that stretches backward for millions of years. The chemistry here is different too. The deep sediments are enriched with elements drawn down from the upper ocean, trapped in fine layers like pages in a book. Each layer holds clues about Earth's past climate. Ancient plankton shells, volcanic ash, and trace metals that reveal how the planet has changed over ages. In this way, the trenches act as natural archives, recording the story of Earth in silence. For all their remoteness, the Hadal trenches are not lifeless abysses, but fragile sanctuaries. Some are disturbed by deep-sea earthquakes or small landslides, sending plumes of sediment rising like underwater smoke. Others accumulate microplastics and pollutants carried by global currents. Even the deepest point of the Mariana Trench has shown traces of human impact. It's a quiet reminder that no place, however remote, is beyond our reach. And yet, despite these intrusions, the trenches remain among the most pristine and awe-inspiring places on the planet. They are reminders of the Earth's restlessness, living evidence that the surface we stand on is not static, but constantly reshaped. They show that even in the darkest, most pressurized and isolated corners of the world, life refuses to vanish. The Hadal realm is the Earth's deepest secret, a place where the planet folds into itself, where light has never been, and where every living thing is both fragile and indestructible at once. Down there, pressure, darkness, and time blend into a single stillness. It is the sound of the planet thinking slowly, in kilometers of silence. Deep beneath the ocean, where the seafloor cracks and shifts, fire meets water in one of Earth's strangest contradictions. Here, the edges of tectonic plates, boiling fluids burst from the crust into near-freezing seawater, creating shimmering towers of mineral and steam. These are hydrothermal vents, the ocean's hidden forges, where geology and biology intertwine in a dance of heat, chemistry, and life. Most vents form along the great mid-ocean ridges, mountain ranges that snake around the globe for more than 60,000 kilometers. Along these ridges, the Earth's crust is constantly spreading apart, opening gaps where molten rock pushes upward. Seawater seeps into these cracks, heats to hundreds of degrees Celsius, and then surges back out, loaded with dissolved minerals and gases. When this scalding water meets the near-freezing sea, those minerals instantly precipitate, forming towering chimneys that billow dark plumes. These structures, known as black smokers, can rise as tall as 10-story buildings, their columns growing and collapsing over years like living volcanoes made of metal. Not all vents are so dramatic. Some release cooler, slower flows of fluid that emerge as shimmering, almost invisible currents. These are called diffuse vents. And while they lack the theatrical black plumes, they host dense oases of life. The chemistry is different. Gentler gradients of heat and minerals, but for many species, these are the perfect conditions. Together, black smokers and diffuse vents make up a patchwork of microhabitats, each one offering a unique recipe of temperature, pH, and dissolved elements. The real magic of these places isn't the heat, but the chemistry. Where sunlight cannot reach, chemical gradients take its place. The vent fluids are rich in compounds like hydrogen sulfide, methane, and iron, all of which can be oxidized to release energy. Microbes living here perform chemosynthesis, turning those chemical reactions into food in much the same way plants turn sunlight into sugar. Instead of green chlorophyll, they rely on enzymes that strip electrons from these chemicals, capturing energy molecule by molecule. It is sunlight's mirror image, life powered not by the sky, but by the Earth's own breath. Around these microbial engines, entire ecosystems flourish. Giant tube worms, sometimes 2 meters long, form dense forests that wave gently in the vent currents. They have no mouths, no stomachs, and no digestive tracts at all. Inside their bodies live symbiotic bacteria that perform chemosynthesis for them, producing sugars from the vent's sulfur-rich water. In return, the worms provide shelter and the steady flow of chemicals the bacteria need. It's a living partnership, a plant-animal hybrid, though no sunlight is involved. Other creatures take different approaches. Vent mussels and clams harbour bacteria within their gills, feeding them sulfide from the vent fluids. Some shrimp species carry their microbial partners directly on their shells, grazing them like gardeners tending a crop. Crabs, fish, and an entire cast of scavengers follow close behind, feeding on the abundant life these microbes sustain. In a sense, the bacteria are the farmers of the deep, and everything else is just living off their harvest. These vent communities grow quickly, often blooming in a matter of months after a new vent opens. But their world is unstable. A vent can vanish overnight if the flow shifts or the chimney collapses. The animals that live here must adapt not only to heat and pressure, but to constant change. Many species produce larvae that drift with the currents, searching for another active vent, a new patch of seafloor where the conditions are just right. In this way, life here is both ancient and perpetually young, always rebuilding itself from the planet's geological breath. The scale of this energy exchange is extraordinary. The vent fluids may emerge at temperatures of 400 degrees Celsius, but because of the immense pressure, they do not boil. Instead, they mix instantly with cold seawater, forming zones where temperature can change by hundreds of degrees in the space of a meter. These steep thermal gradients create endless opportunities for chemistry to happen. Minerals like pyrite and anhydrite crystallize in moments, coating the chimneys with glittering metallic layers. Iron and copper precipitate into clouds of black dust, the smoke that gives black smokers their name. The minerals don't just build chimneys, they also feed life indirectly. When the metal-rich plumes settle on the seafloor, they alter the chemistry of surrounding sediments, creating new niches for microbes. Even the dead chimneys, the ones that have cooled and stopped venting, remain habitats for years, slowly colonized by sponges and corals that feed on the faint residue of what was once a roaring furnace. Hydrothermal vents are also windows into Earth's early past. The conditions around them, hot water, minerals, and energy gradients, resemble what scientists think existed on the young Earth billions of years ago. Many researchers suspect that life itself may have begun in places like these, with simple molecules forming on the surfaces of minerals and evolving into the first living cells. In this way, modern vents are not just ecosystems, they are living time machines showing how chemistry can turn into biology. Despite their alien beauty, hydrothermal vents are fragile. They are patchy, scattered across thousands of kilometers, and often short-lived. Some last only a few decades before going dormant. When one dies, its community fades and another begins elsewhere, following the movement of its tectonic plates and magma chambers. For animals that depend on them, the ocean is a patchwork of fleeting islands. Finding a new vent before the old one cools can mean the difference between survival and extinction. And yet, when a new vent opens, life finds it astonishingly fast. Within weeks of an eruption, microbial mats begin to spread, followed by worms, clams, and crustaceans. Scientists have seen vents recover from total destruction in under a year. It's as if the ocean carries a memory of these places, seeds of life waiting to bloom wherever the conditions appear. For humans, these sites have become a source of wonder and curiosity. The first vent, discovered in 1977 near the Galapagos Rift, changed biology forever. Until then, no one had imagined that sunlight-free ecosystems could exist on Earth. Today we found hundreds more, from the Pacific to the Atlantic, and even in the Arctic Ocean. Each discovery reminds us that life's reach is far greater than we once thought. In recent years, scientists have also realized that vents influence the planet in subtle but significant ways. They help cycle metals and minerals through the ocean, affect the chemistry of seawater, and even play a role in regulating carbon. They connect the inner Earth to the outer ocean, acting as natural vents for the planet's energy and material. It's humbling to think that beneath kilometers of cold water, the Earth is constantly exhaling, releasing heat, minerals, and possibilities. From that breath, entire communities emerge, thrive, and vanish, only to rise again elsewhere. Hydrothermal vents are the perfect paradox, born from fire, sustained by water, and ruled by chemistry. They show that life doesn't need sunlight or comfort, only contrast, where hot meets cold, where chaos meets calm, where the planet's breath meets the sea. Something always finds a way to live. And in the silent dark, surrounded by mineral towers and shimmering currents, it's hard not to feel that these hidden furnaces are the ocean's own heartbeat, pulsing quietly beneath the world. Far from the fiery heat of hydrothermal vents lies a quieter world of chemistry, one that seeps rather than erupts, glows cold instead of hot, and sustains life at a slower, steadier pace. These are the cold seeps, the ocean's subtle breath, where methane and hydrogen sulfide leak silently from the seafloor. They are places of stillness and patience, where energy seeps out of the earth like whispers through cracks in stone. A cold seep might not look like much at first glance. To a submersible's camera, it appears as a patch of pale sediment or a shimmer in the water, as though heat is rising from below. But look closer, and you might find something extraordinary: a brine pool, an underwater lake resting at the bottom of the sea. These pools are formed from dense salty water that has collected in depressions on the seafloor. They don't mix with the surrounding seawater, so their surfaces ripple like liquid mirrors. Some are so rich in methane and salt that they appear oily or glassy, reflecting the dim light from a submersible like a pond on the moon. The chemistry at these seeps is unlike anywhere else on Earth. Methane and sulfide, both products of the planet's buried metabolism, escape through cracks and sediments. They form the energy base for entire ecosystems that, like those at hydrothermal vents, depend on chemosynthesis rather than sunlight. But while vents burn bright and brief, cold seeps are the slow embers, stable, long-lived, and deeply entrenched in the geology around them. The secret to their endurance lies in the way gases like methane behave under pressure. When methane rises from deep within the crust, it encounters cold seawater and immense pressure. Under these conditions, the gas combines with water molecules to form methane hydrates, a strange crystalline substance that looks like ice but burns when lit. Sometimes called fire ice, it locks vast amounts of carbon beneath the seafloor. In fact, methane hydrates may store more energy than all known fossil fuels combined. In the depths of the ocean, these hydrates form delicate frameworks within the sediments, stabilizing them like cement. But they are fragile. A slight change in temperature or pressure can cause the crystals to break apart, releasing methane bubbles that rise toward the surface in long, shimmering streams. Scientists call these methane seeps, and from a distance they look like columns of silver pearls drifting up through the dark. Around each seep, life gathers quietly. Bacteria and archaea thrive at the boundary between oxygen-rich seawater and the oxygen-poor fluids escaping from below. These microbes form mats that look like thin, white snow or golden filaments spread across the mud. They use the chemicals in the seep, oxidizing methane or sulfide, to make organic matter. As with hydrothermal vents, these microbes are the foundation of the food web. Above them live the symbiotic animals, mussels, clams and tubeworms that host the bacteria inside their tissues. The worms extend their red plumes into the water to draw in oxygen and sulfide, which their internal partners then use to create nutrients. The mussels, meanwhile, open slightly to expose their gills, where similar bacteria perform their quiet alchemy. It's a partnership built not on speed but on steadiness, as these animals may live for decades in the same patch of seabed. feeding on a chemistry that never rushes. Unlike the chaotic heat of vents, where plumes roar and communities appear and vanish within years, cold seeps are serene. Their chemical leaks can persist for centuries, even millennia. The result is an ecosystem that moves in slow motion. Colonies grow gradually, layer upon layer, building what scientists call chemosynthetic reefs, not made of coral or algae, but of shells and bones cemented by bacteria. Some seeps in the Gulf of Mexico, for example, are surrounded by mounds of fossilized shells from generations of mussels and clams that lived and died in the same spot. Among the most haunting features of these regions are the brine pools, those dense saline basins that look like small inland seas on the seafloor. To the untrained eye, they appear almost alive, their surfaces rippling gently beneath the weight of the ocean above. The boundaries between the pool and surrounding water are sharp, so sharp that small fish and crustaceans can be seen swimming down toward them and then suddenly floating back up, stunned by the lethal chemistry. The brine is so dense and oxygen-poor that few animals can survive within it. Yet just at the edges, where the two layers meet, life flourishes. Tube worms and mussels cluster along the boundary like plants along a shoreline, harvesting the chemical contrast between one world and another. It's this contrast, not heat or light, that drives the deep sea's cold seeps. Where hydrogen sulfide or methane meets oxygen, energy is released and life takes hold. These reactions happen at a glacial pace, but in an environment where stability is rare, slowness is an advantage. The communities here are some of the oldest continuous ecosystems on the planet, quietly thriving in the same locations for thousands of years. Cold seeps also act as the ocean's subtle regulators. Methane, a potent greenhouse gas, is trapped and consumed by microbes before much of it can escape to the surface. The bacteria living here are, in a sense, guardians of the climate, recycling carbon and locking it away in sediments. Without them, vast amounts of methane might rise into the atmosphere, altering the planet's balance. For scientists, these seeps are treasure troves of information. They reveal how life can exist in complete darkness, sustained by chemistry rather than light, and they may offer clues to where life could exist elsewhere in the universe. Icy moons like Europa and Enceladus may have similar interactions between rock and water, producing chemical energy that microbes could use in the same way. Studying Earth's cold seeps helps us understand not just our own oceans, but the potential for life on worlds far from the sun. Despite their calm, there's drama in their stillness. You can almost imagine the landscape, the soft glow of submersible light sweeping across pale sediments, bubbles of methane rising like champagne, colonies of worms swaying in slow motion. No bright colours, no roaring plumes, just the quiet hum of chemistry at work. It's an alien beauty, subtle but mesmerising, where even the smallest reaction becomes the heartbeat of an entire ecosystem. In many ways, cold seeps are the deep sea's counterpart to hydrothermal vents, the cold flame to the vent's fire. One blazes hot and brief, the other glows dim and enduring. Both remind us that life needs only energy, not sunlight, and that energy can take many forms. Whether it comes from molten rock or frozen gas, from heat or from cold, life will always find the gradient and follow it. So beneath the calm of the ocean's surface, hidden in its quietest corners, there burns a slow and steady light, invisible but vital. Cold seeps may not roar like volcanoes or shimmer like vents, but they keep the planet's deep chemistry alive, quietly balancing what the Earth exhales and what it keeps. And in that balance, life continues, unhurried, glowing softly in the dark. When a whale dies at sea, its story is far from over. In fact, in the deep ocean, that story is only just beginning. A whale's body, once a soaring shape of grace and motion, becomes something else entirely, a drifting island of life. As it sinks, It carries with it the energy of a lifetime, enough to sustain an entire community for decades. Scientists call this phenomenon a whale fall, and it is one of the most remarkable transformations in the natural world. In a place where food is scarce and change is slow, the arrival of a single whale carcass is like the sudden appearance of a forest in a desert. The deep sea floor, normally quiet and barren, erupts with life. The descent is the first act of this quiet drama. As the body sinks through the water column, becomes a moving banquet. Sharks, hagfish, and other scavengers gather to feed, tearing at the flesh as it drifts downward. Even before it reaches the bottom, the whale's body is surrounded by a procession of creatures following its scent through the dark, a slow-motion migration drawn by chemistry and hunger. When it finally settles on the seafloor, the real transformation begins. The ecosystem that forms around a whale fall unfolds in stages, each one lasting years or even decades. The first is the scavenger stage, a frenzy of activity compared to the stillness that usually reigns down here. Hagfish burrow into the soft flesh, releasing clouds of silt. Giant isopods, the deep-sea cousins of woodlice, crawl across the carcass in their dozens, feeding methodically. Sleeper sharks arrive, their pale eyes gleaming in the submersible lights. Within months, most of the soft tissue is gone, stripped clean by a chorus of mouths adapted to patience and persistence. But what comes next is far more subtle. As the bones are exposed, the enrichment stage begins. The whale's skeleton is soaked in oil and fat, dense reserves of energy that seep slowly into the surrounding sediment. This chemical richness attracts a new wave of inhabitants, worms, clams, and snails that burrow into the bones or cluster around them. These animals, in turn, bring their own microbial partners, bacteria that can break down the complex molecules of whale oil, turning fat into food once more. Around the carcass, the seafloor darkens with organic residue, and the community shifts from a feeding frenzy to a slower, steadier rhythm. The final act is the most mysterious, the sulfophilic stage, named for the sulfur-loving microbes that take over when the bones themselves begin to decay. Deep within the skeleton, bacteria break down lipids and release hydrogen sulfide, the same chemical that powers hydrothermal vents and cold seeps. In doing so, they create a miniature chemosynthetic ecosystem right there on the bones. Tube worms and mussels that normally live near vents begin to appear, drawn to the chemical energy. Life, once nourished by the whale's flesh, now thrives on its chemistry. In total, a single whalefall can support life for 50 to 100 years. Long after the body has vanished, its influence lingers, a faint enrichment in the sediment, a small rise in microbial activity, a ripple in the slow current of the abyss. The sea keeps nothing wasted. Even death becomes fuel for life, recycled and transformed again and again. Whale falls are rare. The ocean is vast and most whales die near the surface or drift to shallower waters where their bodies are consumed before they can reach the deep. But in those few places where they do sink all the way down, they become beacons of abundance. Scientists have described them as stepping stones across the abyss, isolated oases that allow species to disperse from one to another. The same kinds of worms and mollusks found on whale falls have also been discovered on hydrothermal vents and cold seeps, suggesting that these ecosystems are connected through the slow migration of larvae carried by deep currents. In this way, the death of a whale doesn't just feed a local community, it helps weave the deep ocean together. Each fall becomes part of a larger pattern of renewal, an underwater network built from loss. The discovery of whale falls was relatively recent. Before the late 20th century, scientists had never seen one intact. Then, in 1977, a submersible exploring the seafloor off the coast of California stumbled upon a massive skeleton draped in soft sediment and alive with worms and crustaceans. It was a revelation. Until then, no one had realized that a single animal could give rise to such a complex, long-lasting ecosystem. Since then, dozens more have been found, each one slightly different, shaped by the size of the whale, the depth of the fall, and the chemistry of the surrounding seabed. Among the most extraordinary inhabitants of these sites is the Osedax worm, also known as the bone-eating worm. Discovered in the early 2000s, it has no mouth or stomach. Instead, it grows root-like tendrils that penetrate the whale bones and house symbiotic bacteria. These bacteria digest the fats and oils trapped inside, sharing the nutrients with their host. Some species of Osedax can dissolve bone entirely, leaving behind nothing but delicate tunnels and filigree patterns in the skeleton. It's a quiet, graceful form of decomposition. Life unmaking life molecule by molecule. Even in decay, there's beauty in the rhythm of a whaleful. The cycle is complete, yet unhurried. The energy that once powered migrations and songs now feeds worms, microbes and fish that will themselves one day become part of the same endless loop. It's a story of transformation, not tragedy. A reminder that in the deep sea, nothing truly ends. It simply changes form. Whalefalls also hint at how connected the ocean really is. The whale that sinks in the Pacific may have fed for decades on krill that grew from nutrients carried by rivers thousands of kilometers away. In death, it returns that energy to the sea, to be taken up again by creatures it will never meet. Every link in that chain depends on the others. For all their importance, these falls are invisible to us. They happen in silence under immense pressure, without witnesses except for the creatures that live there, and yet they are vital to the ocean's balance. In a world that often seems driven by endless consumption, the deep sea reminds us that nothing is lost. Energy only changes hands. If you could drift past one of these sites, it would feel almost sacred. A cathedral of bones surrounded by a soft snow of detritus, lit only by the faint glow of bioluminescent life. Around the ribs and vertebrae, worms sway like grass in a deep-sea meadow. Crabs move carefully, as though aware of the gravity of the place. Even the scavengers seem subdued, their work deliberate, respectful. Whale falls are the ocean's quiet memorials, not of loss, but of continuity. They show that the deep sea, though cold and dark, is never lifeless. It breathes, eats, and rebuilds itself endlessly. A whale's journey ends not with shunts, but with renewal. Its body becomes a home, its bones a reef, its energy the seed of countless new beginnings. Down there, among the silt and shadows, death feeds life, and the story of the sea goes on. Deep in the cold, dark reaches of the ocean, far beyond the touch of sunlight, rise forests built not of wood or leaves, but of stone and living bone. These are the cold water corals, vast branching colonies that grow in silence, sculpting ancient architectures on the seafloor. Unlike their tropical cousins, they don't rely on sunlight or colourful algae. Instead, they feed on what the ocean delivers, a slow rain of plankton and organic dust drifting through the dark. It's easy to imagine coral reefs as something bright and shallow, teeming with fish and glowing in the sun, but the truth is that most of Earth's coral species live in total darkness. Cold water corals exist from just a few hundred meters deep to beyond 2,000, forming structures that can stretch for kilometers along the slopes of underwater mountains. Some of these reefs are older than recorded human history, growing at a rate of just a few millimeters a year, patient builders in a world without hurry. The best known of these architects is Lophelia pertusa, a pale branching coral that forms immense reefs in the North Atlantic. Each tiny polyp builds a calcium carbonate skeleton, linking with its neighbours to create a sprawling framework of living stone. Over centuries, layer upon layer of coral rises, twisting into intricate shapes that resemble forests frozen in mid-motion. Where tropical reefs pulse with light and colour, These ones glow faintly white in submersible beams, their surfaces dusted with drifting sediment like snow on winter trees. They thrive where the seafloor is rough and the current strong, along continental slopes, seamounts, and underwater ridges. These places act like windbreaks in the deep, redirecting the slow flow of water and concentrating tiny bits of food. Plankton, organic debris, and marine snow all gather in these currents, forming a steady supply of nutrients. The corals extend their delicate tentacles into the passing stream, catching particles one by one. Each meal is minuscule, but over centuries it builds cathedrals of life. Alongside them grow sponges, some of which can live for thousands of years. These sponges are not the soft, porous bath sponges we imagine, but intricate networks of silica, glass sponges, literally built from sand. Their forms range from delicate fans to latticed vases that filter seawater with incredible efficiency. A single sponge can pump hundreds of litres of water through its body each day, capturing microscopic food while helping to clean and circulate the surrounding water. In the deep, even the act of feeding becomes a kind of quiet engineering. The combination of corals and sponges creates complex habitats that shelter countless other creatures. Fish find hiding places among the coral branches, shrimp and crabs cling to the skeletal frameworks, and brittle stars crawl over the surfaces like stars moving through a frozen sky. In these forests of stone, every ledge and crevice offers a home. The biodiversity rivals that of the most vibrant tropical reefs, though here the palette is muted, whites, greys, and faint oranges glowing under the soft glare of a submersible's light. The fragility of these structures is striking. Each coral branch, though made of stone, is brittle and easily broken. A single drag of a trawling net can destroy centuries of growth, and yet, despite their vulnerability, these reefs persist in places where almost nothing else can. They endure crushing pressure, freezing temperatures, and near total darkness. Their secret is time. In the deep ocean, where change comes slowly, longevity is the ultimate adaptation. Some individual coral colonies have been dated at over 4,000 years old, older than the Great Pyramid of Giza. Their growth is so gradual that even a small reef can represent millennia of continuous construction. Every polyp lives, dies, and leaves behind its skeletal legacy, becoming the foundation for the next generation. The reef grows upward and outward, layer by layer, a monument to persistence. Seamounts, the undersea mountains that dot the ocean floor, are particularly rich in these ancient reefs. Rising thousands of meters from the abyssal plains, they intercept deep currents that sweep nutrients upward. Where those currents hit the rocky slopes, they slow, deposit their loads of food, and create a perfect environment for coral growth. Over time, the seamounts become oases of life, isolated worlds where species evolve in quiet independence, many found nowhere else on Earth. Because sunlight never reaches these depths, the energy flow here depends entirely on what drifts down from above. Every bit of organic matter, every microscopic fragment of dead plankton, becomes part of the deep's patient economy. The corals capture it, the sponges filter it, and the creatures that live among them pass it along the chain. Nothing moves quickly, but everything moves purposefully. It's a system built not on abundance, but on continuity. Cold water coral reefs are also crucial for the wider ocean. They act as nurseries for fish species that later migrate into shallower waters, replenishing ecosystems that humans depend on. Their intricate structures slow currents and trap sediments, helping to stabilize the seafloor. And as they grow and die, they store carbon in their calcium skeletons, locking it away for millennia. In this sense, they are not only habitats, but also quiet climate engineers. Exploring these reefs feels like visiting another planet. The light from a submersible cuts through the darkness to reveal what looks like a frozen forest, pale branches arching over the seafloor, their tips swaying in slow motion with the current. The silence is complete except for the faint hum of equipment and the occasional crack of coral shifting under its own weight. There is a sense of peace here, but also of awe, as if the ocean itself is holding its breath. Scientists are only beginning to map how widespread these reefs truly are. Discoveries in recent decades have revealed vast systems stretching across the North Atlantic and around the edges of the Pacific. In some regions, these reefs cover areas larger than cities, hidden for millennia beneath layers of darkness. Others have been found thriving off the coasts of Antarctica, proving that even the coldest waters on Earth can sustain this slow, delicate life. Yet their fragility makes them vulnerable to human activity. Bottom trawling, mining, and deep-sea cable laying can shatter these ancient structures in minutes. Once damaged, they take centuries to recover, if they recover at all. The deep sea is resilient, but it is not invincible. For ecosystems that measure their growth in millimeters per year, time is both a gift and a risk. Still, the quiet endurance of these coral forests is reassuring. They remind us that the ocean is always building, always renewing itself, even in the most unlikely places. Where no sunlight shines and no tides stir, life still finds a way to construct beauty. Not in bright bursts, but in patient whispers of stone. If you could drift above one of these reefs, you would see a landscape sculpted by time itself. Delicate spires of coral rise from the seafloor like the ruins of an ancient city, each branch recording centuries of quiet persistence. Sponges shimmer faintly in the current, their forms ghostly but alive. And everywhere tiny creatures move, slow, cautious, enduring, among the cold, ancient architecture of the deep. In that darkness there is no rush, no competition, no noise, only the steady, hushed rhythm of building and being. The deep ocean does not hurry, and neither do its architects. They have all the time in the world, and they use it to create something truly timeless. Life turned to stone, and stone turned back to life. The deep sea may look empty, but it's ruled by the smallest inhabitants imaginable. Microbes. Invisible, ancient, and tireless, they are the true engineers of the ocean, quietly running its chemistry and keeping the planet's systems in balance. Without them, every other creature, from giant squid to coral polyps, would simply stop. They are the ocean's unseen workers, weaving together the cycles of carbon, nitrogen, sulfur, and life itself. Microbes are masters of chemistry. Where larger creatures need sunlight or food to survive, microbes make their own rules. They live by swapping electrons, tiny particles of energy that move between molecules in what scientists call redox reactions. The name sounds complicated, but the idea is simple. One chemical gives up electrons, another takes them, and energy is released in the process. It's the same fundamental exchange that happens in your own cells every time you breathe or digest food. Only down here it happens without oxygen, light, or warmth. In the deep ocean, microbes use whatever the Earth gives them: hydrogen, sulfur, methane, iron, even rock itself, as their source of energy. Some oxidize hydrogen sulfide bubbling up from the seafloor, turning toxic gas into food. Others breathe metals, using manganese or iron instead of oxygen. A few live off the slow decay of radioactive elements buried in the crust. To them, it doesn't matter whether energy comes from the sun or from the planet's molten heart. As long as there's a chemical imbalance to exploit, they can make a living. These tiny chemists are astonishingly adaptable. Many of them are extremophiles, organisms that flourish in conditions that would destroy most life. Some thrive at temperatures near boiling, around hydrothermal vents, while others prefer the icy stillness just above freezing. Some survive crushing pressures that would flatten a submarine, and others live in waters so acidic or alkaline that nothing else could. Their enzymes, The biological machines that power their reactions are fine-tuned to these extremes. Under pressure, the folds of an enzyme might collapse, but in these microbes, the structures are built to flex instead, working smoothly where physics itself seems to break down. This flexibility isn't just survival, it's innovation. Microbes have invented more metabolic tricks than all plants and animals combined. They can store energy, share it, and recycle it in endless loops that shape the chemistry of the whole planet. The oxygen you're breathing right now exists because ancient microbes learned to split water molecules billions of years ago, releasing oxygen as waste. The nitrogen in your DNA has passed through countless microbial hands, transformed again and again by bacteria in the soil and the sea. They are the original engineers, and the rest of life simply builds on their blueprints. In the deep ocean, where nutrients are scarce, microbes have become architects of efficiency. They live in communities called biofilms, where millions of cells stick together on surfaces like rocks, sediments, or even the shells of other creatures. A biofilm is like a microscopic city, layers of residents connected by chemical communication, sharing resources and protecting each other from the surrounding environment. The outer cells face the current, handling the flow of nutrients, while those within focus on storage or repair. Waste from one layer becomes fuel for another, and together they create a miniature ecosystem of astonishing complexity. You can think of these biofilms as the ocean's slow, patient scaffolding. They coat almost every surface below the light zone, binding sediments and forming the foundation for larger organisms to settle. Without them, the seafloor would be a far less stable place, a shifting desert of silt. Some corals and sponges even rely on microbial films to establish their first foothold, making these microbes the literal groundwork for entire deep-sea ecosystems. One of the most fascinating things about these microbial worlds is how they recycle the ocean's chemistry. Through a network of biogeochemical loops, they keep the deep sea and the planet balanced. One group consumes methane leaking from a cold seep, converting it into carbon dioxide. Another uses that carbon to build organic molecules. A third breaks those molecules back down, releasing nutrients that drift upward to feed plankton near the surface. Every element, every atom cycles endlessly, passing from one form of life to another in a system that has run flawlessly for billions of years. Even death is no obstacle to their work. When a whale falls to the ocean floor, microbes are among the first to arrive, breaking down tissues and releasing nutrients that sustain larger creatures. When hydrothermal vents cool and go dark, microbial mats persist long after, digesting minerals and maintaining life until the next source of energy appears. They are quite literally the continuity of life in the deep, bridging every interruption, every extinction, every quiet period of Earth's history. To study them, scientists often rely on indirect clues, traces of their metabolism left in the chemistry of the water, or genetic fingerprints extracted from sediment samples. Under the microscope, these organisms look unassuming, simple rods, spheres, or spirals drifting in a drop of water. But beneath that simplicity lies incredible sophistication. A single microbial cell can sense its environment, move toward or away from chemical cues, and coordinate its behavior with billions of others. Some even exchange genetic material directly, sharing useful adaptations like neighbors lending each other tools. Their resilience borders on the unbelievable. Microbes have been found kilometers beneath the seafloor, living in rock pores where nutrients arrive only once every 1,000 years. Others have been recovered from deep sediments dated to tens of millions of years old, still alive, still metabolizing at an imperceptibly slow pace. It's a reminder that time means little to them. They can afford to wait. Because microbes are so small, their collective impact can be hard to imagine. But taken together, They outweigh all animals on Earth combined. They regulate the chemistry of the atmosphere, the fertility of the oceans, and the composition of the rocks themselves. They are the invisible majority, setting the rules that everything else must follow. And they don't just live in the ocean, they are the ocean. A litre of seawater can contain more microbial cells than there are people on the planet. Each one is a tiny experiment, a different solution to the problem of existence. Together, they create an ocean-wide network of chemical exchanges, shaping currents, nutrient cycles, and even climate. For all their importance, microbes are rarely noticed. They have no eyes, no sound, no colour. They drift and divide in silence, unseen but indispensable. Yet if they were to stop, everything else would follow. Oxygen would fade, carbon would build up, and the planet's rhythms would grind to a halt. In many ways, the deep ocean belongs more to them than to anything else. The great fish and glowing jellies are only temporary guests in a world that microbes have ruled for billions of years. They were the first to harness energy from the Earth's chemistry, the first to build ecosystems, and the first to shape the planet into something habitable. Everything that came after, coral reefs, whales, and even us, is part of their legacy. The next time you think of the deep sea as empty, imagine the invisible multitudes that make it run. The tireless chemists swapping electrons, building cities of film and slime, and keeping the planet's machinery turning quietly in the dark. They are not just the first engineers of Earth, they are its eternal ones, still down there, still at work, writing the laws of life one molecule at a time. In the deep sea, evolution moves at the pace of a drifting current. Down here, life unfolds so slowly that time itself feels like part of the environment, a habitat as real as rock or water. Energy is scarce, change is rare, and the rules that shape life above the waves lose their urgency. The creatures that live here are shaped not by speed or competition, but by endurance. They grow slowly, reproduce rarely, and evolve in rhythms measured not in generations, but in geological ages. The first thing to understand about evolution in the deep ocean is that energy is everything. On the surface, sunlight pours down, fueling fast metabolisms and quick life cycles. Plants grow, animals eat, and the wheel of life spins rapidly. But in the abyss, energy arrives only as a faint drizzle, the soft snow of organic debris falling from above. Each flake of marine snow is precious, and every creature must stretch its value as far as possible. As a result, metabolism slows, and with it the tempo of life. A deep-sea fish may take decades to reach maturity. Some corals live for thousands of years, adding only a millimetre or two of growth each year. The Greenland shark, drifting through the cold North Atlantic, grows so slowly that a human might live and die before the shark adds half a metre in length. These animals do not rush to adapt or change, they wait, persisting through the shifting age of the planet. Evolution still happens, of course, but it happens in slow motion, each new trait honed over centuries rather than seasons. Isolation also plays a role. The deep sea is not a single continuous world, but a vast mosaic of habitats, trenches, seamounts, vents, plains and slopes, separated by enormous distances. Many species live their entire lives in a single region, never crossing the invisible borders of pressure, temperature, and chemistry that define their world. Populations become cut off from one another, evolving separately in silence. Over time, they diverge, creating new species found nowhere else. The result is a strange paradox. The deep ocean is both incredibly stable and endlessly diverse. Some of its inhabitants are living relicts, survivors of ancient lineages that have vanished everywhere else. The coelacanth, for example, a lobe-finned fish thought to have gone extinct 70 million years ago, still patrols the depths off the coasts of Africa and Indonesia. Its slow heartbeat and heavy, Oil-filled bodies suit it perfectly to the deep, designed so well balanced that evolution simply stopped tinkering. Other creatures, like certain species of sea lilies and glass sponges, look almost identical to their fossil ancestors from the Paleozoic era. In their stillness, the deep sea preserves not just life but history. But alongside these relics are the novelties, entirely new forms born of isolation and innovation. The crushing pressure, lack of light, and constant cold have forced evolution down unique paths. Some animals have lost their eyes entirely, trading vision for heightened sensitivity to vibration or smell. Others have evolved bioluminescence, turning darkness into communication. Deep-sea anglerfish, with their eerie lures and symbiotic males, are examples of evolution's creativity under constraint. Their world may change slowly, but that doesn't mean it stands still. It simply experiments in subtler, stranger ways. Dispersal in such an environment requires ingenuity. Most deep-sea species can't travel long distances as adults, so they rely on larvae to carry their lineages across the abyss. Tiny, buoyant, and often transparent, these larvae drift with the currents for months, sometimes years, before settling in a suitable patch of seafloor. Some may end up thousands of kilometers from where they began. It's a quiet lottery played out in slow motion, countless invisible travelers carried by deep currents, each one a potential founder of a new population. Even objects can become vehicles for dispersal. Sunken wood, whale bones, or volcanic rocks serve as rafts, carrying microbial communities and small invertebrates between habitats. When a hydrothermal vent shuts down, its inhabitants may hitch a ride on a drifting plank or piece of pumice, eventually colonizing a new vent thousands of kilometers away. The ocean's stillness hides a delicate web of movement, where even in the deep, life refuses to stay confined. What makes the deep sea so remarkable is that it serves as both a museum and a workshop, a place where ancient lineages endure and new experiments quietly unfold. The stability of its environment allows old designs to persist for eons, while its isolation fosters innovation in pockets scattered across the globe. Every vent, every French, every coral mound is its own evolutionary stage, running a play that began millions of years ago and is still unfolding. Consider the creatures that live near hydrothermal vents. Each vent system is temporary, lasting perhaps a few decades before the geological plumbing shifts. The organisms that depend on them, tube worms, clams, shrimp, must either find new vents or vanish. To survive, they've evolved remarkable reproductive strategies, producing larvae capable of drifting enormous distances through the deep currents. The same genes that help them thrive in heat and pressure also allow them to endure the long, cold voyage between oases. It's evolution under pressure, literally and figuratively. Meanwhile, in the abyssal plains, where stability reigns for millions of years, creatures evolve in the opposite direction, toward conservation. Here, small changes can persist indefinitely. Some species of sea cucumber or brittle star may differ little from their ancestors of the Jurassic era. Their slow pace of life, combined with the constancy of their surroundings, creates a kind of biological time capsule, evolution at rest. The deep sea's slow evolutionary tempo also means that extinction and creation happen at a different rhythm. On land, environmental shifts can wipe out species in an instant. In the deep, where change takes longer to arrive, extinction tends to creep rather than strike. When conditions do shift, through tectonic movement, sediment flow, or climate-driven chemistry, the response is gradual, unfolding over thousands of years. Evolution here is less a race and more a negotiation, a patient dialogue between life and the planet's deep processes. Yet the deep sea is not immune to change. Even subtle alterations at the surface, warming waters, acidifying oceans, declining oxygen levels, can eventually reach the abyss. The same slowness that once protected these ecosystems now makes them vulnerable. Species that took millions of years to adapt may not adjust fast enough to the pace of human-driven change. In that sense, the deep sea's patience is both its strength and its weakness. To think of evolution in the deep ocean is to stretch your sense of time. Imagine generations unfolding like slow waves overlapping over centuries. Picture a coral colony that began before cities were built, still quietly expanding, polyps giving way to new polyps in an unbroken lineage. Picture a snailfish evolving to fit the contours of a trench, its genes fine-tuned to the chemistry of a single, narrow world. Every adaptation here is a whisper, every mutation a step taken in near silence. If you could speed it up, the deep sea would look like a vast glowing organism in slow motion. Species appearing and fading like embers, drifting apart, reconnecting through currents, shaping and reshaping themselves against the steady pull of time. It's easy to think of evolution as competition, but down here it's more like endurance art, a patient process of refinement that rewards balance over aggression, efficiency over excess. The deep ocean is often described as alien, but in truth it's the most ancient part of the planet, still operating on the original rules of life. It shows that evolution doesn't need to be fast to be creative. It just needs time. And in the deep, time is abundant. Here, every creature, every lineage, every chemical pathway is part of a quiet masterpiece billions of years in the making. In this slow-motion world, life doesn't rush to change. It listens, adjusts, and endures. It waits for the right moment, the right current, the right mutation. Evolution in the deep is not a sprint toward progress. It's a conversation with eternity, one that's been going on since the first cell drifted through the first sea, and one that, if left undisturbed, will continue long after we're gone. For most of human history, the deep sea was a mystery we could only imagine. It was a place of legends, home to monsters, lost cities, and endless darkness. The ocean floor seemed as unreachable as the moon, and yet quietly, patiently, humanity began to look downward instead of upward, sending small, fragile machines into the abyss to see what lay beneath the waves. What we found there wasn't terror or emptiness, but wonder. A world that had always been part of our planet, waiting in silence. The story of deep-sea exploration begins with sound. Long before we could see the seafloor, we learned to listen to it. In the late 1800s, scientists began using weighted lines and early sonars, sound waves sent through water to measure depth. Each ping that echoed back revealed a little more of the ocean's shape, its mountains, plains, and trenches. These primitive tools gave us the first glimpse of the world beneath the surface, showing that the seafloor was anything but flat. It had ridges higher than the Alps and valleys deeper than Everest. But seeing it directly required courage and invention. In the 1930s, engineer Otis Barton and naturalist William Beebe built the bathysphere, a steel sphere just big enough for two people. Suspended by a cable and lowered from a ship, it had tiny portholes no larger than dinner plates and walls thick enough to withstand crushing pressure. In 1934, they descended to more than 900 meters off Bermuda, a record at the time. Peering through the glass, they saw glowing jellyfish, strange fish, and life forms that no one had imagined. It was the first human eye contact with the deep. Over the decades, new machines pushed further. In 1960, the bathyscaphe Trieste, designed by Jacques Piccard and Auguste Piccard and piloted by Don Walsh and Jacques Piccard, made history. It descended nearly 11,000 meters into the Mariana Trench, to a place now called Challenger Deep, the deepest known point on Earth. The journey took 5 hours down and 3 hours back up. When they reached the bottom, they saw something extraordinary, a small flat fish gliding slowly over the mud. Even at the planet's deepest point, life endured. Since then, exploration has evolved from bravery in small steel capsules to precision guided by technology. Modern crewed submersibles like Alvin Shinkai 6500, and limiting factor can dive to thousands of meters with relative ease. They carry cameras, robotic arms, and sensors capable of measuring temperature, pressure, and chemistry in exquisite detail. The pilots sit in small spheres surrounded by electronics and viewports, navigating a world of blackness illuminated only by their own lights. To look out of those windows is to glimpse a place no sunlight has touched in millions of years. But humans can't be everywhere, and so we built eyes that don't need oxygen, ROVs, or remotely operated vehicles. These robotic explorers are connected to their ships by long tethers of fiber optic cable, allowing scientists to control them in real time. They can descend deeper than any human, hover with precision, and manipulate delicate instruments with robotic arms. Some are small and agile, perfect for close inspection. Others are large enough to lift rocks or deploy instruments on the seafloor. They can stay down for hours, even days, watching, collecting, and listening. The images they send back have changed our relationship with the ocean. Instead of flat maps, we now see moving worlds, glowing vents, drifting creatures, forests war elf in the dark. High-definition cameras reveal textures, colours and movement that even a diver could never witness. The deep sea, once imagined in myths, now appears on screens in real time, and what we find there is stranger and more beautiful than any legend. Exploring these depths demands care. Every sample taken is precious, and every disturbance can leave a mark that lasts for centuries. Scientists working with submersibles follow strict sampling ethics, collecting only what is necessary and handling specimens as gently as possible. Manipulator arms are designed to mimic the sensitivity of a human hand, lifting delicate corals or scooping sediment without crushing or scattering it. Some submersibles even carry small suction devices to collect tiny creatures without harm. The goal is not to conquer the deep, but to understand it, to visit as guests rather than intruders. Each dive is an exercise in patience. Missions can take 12 or more hours from launch to recovery. With only a few of those hours spent on the seafloor, the descent itself is meditative. Minutes stretch into hours as the light fades. The water grows colder and the pressure mounts. In the cabin, the sound of the ship above disappears, replaced by the occasional creak of metal and the soft hum of instruments. It's a journey, not of noise or adrenaline, but of quiet focus. Even the smallest discoveries feel monumental. Finding a new species, capturing a rare behavior on film, or sampling an unknown mineral can transform our understanding of Earth. Many of the greatest revelations in marine science, hydrothermal vents, deep-sea corals, methane seeps, and even new branches of life, were discovered because someone looked closely with a camera and refused to look away. Sonar has remained one of our most reliable tools. Using sound waves, scientists can map entire stretches of seafloor in stunning detail, revealing mountains, canyons, and plains that no one has ever seen directly. Multi-beam sonar can cover wide swathes, while side-scan sonar creates intricate mosaics that show the textures of the seabed. Together, these technologies have turned the unknown deep into a landscape we can finally visualize, even if only in echoes. And yet, despite all our progress, the ocean still guards most of its secrets. More than 70% of our planet lies beneath water, but less than a quarter of the seafloor has been mapped in detail. Even today, each dive brings surprises. New species, new chemical processes, new shapes carved by the slow sculpting of the planet. The deeper we go, the more we realize how much we don't know. There is a quiet poetry in this kind of exploration. Unlike spaceflight with its rockets and spectacle, deep-sea exploration happens in whispers. The submersible sinks slowly, almost peacefully, descending through blue, then black. When it reaches the bottom, its lights reveal a world untouched by time. A cloud of shrimp scatters, a sea cucumber drifts past like a ghost. The pilot, watching through a glass bubble only a few centimeters thick, might be the first and last human ever to see that particular spot on Earth. It is exploration stripped of noise, not conquest, but curiosity. Each dive is a conversation between human ingenuity and nature's oldest mystery. The machines we send down are fragile, but they carry our questions with them. What lives here? How did it begin? How does it endure? Every answer leads to more wonder. There are dangers, of course. The pressure at great depths is relentless, and a small malfunction can end a mission. Electronics corrode, cables tangle, and navigation is often guesswork in a world without landmarks. These challenges are part of the appeal. To explore the deep is to accept uncertainty, to trust technology, teamwork, and patience against a realm that does not forgive haste. When each dive ends and the submersible surfaces, the scientists aboard often speak softly, almost reverently, about what they've seen. The first glimpse of the horizon after hours of darkness feels like waking from a dream. The footage is reviewed, the samples preserved, but the memory of that quiet world lingers. Humanity's journey into the deep is still in its infancy. New technologies, autonomous vehicles, ultra-sensitive sensors and machine learning are allowing us to map and study the ocean as never before. But the heart of it remains the same. A small group of people peering into darkness, driven by the simple need to know what's there. The deep sea doesn't reveal its secrets easily, but that's part of its beauty. It invites curiosity and rewards patience. Every descent is a reminder that even on our own planet, vast frontiers remain, not on other worlds, but beneath our feet. And as long as there are questions left to ask, we'll keep sending our little vessels downward, carrying with them that most human of impulses to explore gently wherever light has yet to reach. For all our satellites, telescopes, and instruments, the greatest mystery we face isn't out in space, it's right beneath our oceans. The seafloor covers more than 2/3 of our planet, yet for most of human history we've known almost nothing about its shape. Until recently, the bottom of the ocean was as unmapped as the far side of the moon. But quietly, with sound waves, mathematics, and patient persistence, we've begun to draw the contours of this hidden world. Mapping the ocean is unlike any other kind of cartography. Light cannot reach beyond a few hundred meters, and no human eye can see through the depths. Instead, we use sound, the only tool that travels efficiently underwater. The process begins with something called multi-beam bathymetry, a method where ships send out fans of sound pulses that bounce off the seafloor and return as echoes. By measuring how long those echoes take to come back, scientists can calculate depth. Do this millions of times over a moving grid, and the result is a three-dimensional picture of the seafloor, drawn entirely in echoes. The term bathymetry comes from the Greek words for deep and measure. Each sweep of the ship's sonar creates a swath of data beneath it, like mowing the lawn with sound. The accuracy depends on the frequency and spread of those pulses. Shallow waters use higher frequencies for detail, while deep waters use lower ones that travel farther. By combining these strips of information, scientists create maps showing ridges, valleys, and slopes in shades of depth. What emerges is astonishing. Entire mountain ranges we never knew existed, trenches deeper than the Grand Canyon, and landscapes shaped by millions of years of tectonic motion. But here's the challenge. The ocean is vast, and ships are small. Even with the best technology, a research vessel might cover only a few hundred kilometers a day. At that rate, mapping the entire seafloor would take centuries. So while multi-beam sonar gives exquisite detail where it's been used, most of the ocean remains uncharted in high resolution. To fill in the gaps, scientists have turned to satellite altimetry, a clever way of sensing the shape of the seafloor indirectly. Satellites orbiting Earth can measure tiny variations in sea surface height caused by the gravity of underwater features. A seamount, for example, pulls a bit more water toward it, creating a subtle bump on the ocean's surface, perhaps just a few centimeters high. By detecting these ripples from the orbit, scientists can infer what lies below. The result isn't as sharp as sonar, but it gives a global view, a first draft of the planet's hidden face. To put this in perspective, the best global maps of the seafloor made from satellite data have a resolution of around 5 kilometers per pixel. That means each pixel represents an area larger than some cities. In contrast, sonar mapping from ships can reach resolutions of tens of meters, showing details as fine as individual lava flows or landslide scars. The combination of the two, broad satellite coverage and detailed local surveys, gives us a layered understanding of the deep. Recently, autonomous underwater vehicles, or AUVs, have added a new dimension to mapping. These robotic explorers glide silently through the water, untethered to ships above. Equipped with their own sonar systems, cameras and sensors, they can fly just a few dozen meters above the seafloor, scanning it in extraordinary detail. Because they move slowly and close to the ground, they reveal features even traditional ships might miss. Ripples in sediment, hydrothermal chimneys, or the faint traces of animal burrows. When the AV resurfaces, it uploads its data, a high-resolution portrait of a small corner of the unknown. The result of all these methods is a planet slowly coming into focus. Each year, new ridges, seamounts, and underwater landslides emerge from the data. Some seamounts rise thousands of meters from the abyssal plains, yet have gone unnoticed until now. Others turn out to be extinct volcanoes, their summits flattened by ancient erosion. Even vast landslides have been discovered, frozen in time, evidence of submarine avalanches that reshaped coastlines long before humans existed. These discoveries aren't just geographical curiosities. They help us understand earthquakes, tsunamis, and the flow of nutrients that sustain ocean life. One of the most exciting aspects of this work is how it connects disciplines. Geologists study the ridges to trace the movement of tectonic plates. Biologists use seafloor maps to predict where coral reefs and sponge forests might grow. Oceanographers use them to model currents and carbon cycles. Even climate scientists rely on bathymetry because the shape of the seafloor determines how heat and water circulate through the oceans, the planet's great thermostat. The more we map, the more we realize how dynamic the seafloor truly is. Volcanoes erupt unseen, building new crust. Canyons widen as sediment slides down their slopes, and deep trenches shift slowly as tectonic plates bend and fracture. Every map is a snapshot of something that's still changing, still alive in a geological sense. It's a quiet reminder that Earth, even in its darkest corners, is never still. There's also comfort in the pace of this discovery. Unlike so many human endeavours that chase speed and finality, mapping the deep is an exercise in patience. The work takes years, even decades. Each pass of sonar reveals just a little more. Each mission adds a few new tiles to the puzzle. Scientists often speak with affection about their data mosaics, overlapping strips of sound and colour stitched together over time. No one person finishes the map. It's a generational collaboration, a conversation between explorers separated by decades. Projects like Seabed 2030, a global initiative to map the entire ocean floor by the year 2030, are continuing this effort. Hundreds of vessels, research institutes and organisations are contributing their data, piece by piece, toward a single shared vision. Every time a ship crosses the sea with a sonar system running, it adds another brushstroke. The ocean's portrait is growing clearer, but it's a painting that will never truly be complete. The deep is always shifting, always rewriting itself. There's something soothing about that. To map the unknown is not to end mystery, but to deepen it. Each new ridge discovered leads to new questions. Why is it here? How old is it? What lives on its slopes? The process is less about finding final answers and more about learning to listen to the echoes of sound bouncing off unseen worlds. If you could see the seafloor map unfold across time, it would look like a slow bloom of knowledge, lines and colours spreading outward from the coasts, filling the blank spaces year by year. The unknown shrinks but never disappears, and maybe that's as it should be. The deep sea doesn't demand haste, it invites curiosity, the kind that grows quietly and endures. Each new contour traced, each mountain revealed, brings us closer to understanding the planet we live on. Yet there will always be another valley just beyond our reach, another echo waiting to return. Mapping the deep is not about finishing the picture, but about celebrating how much more there is to see. The comfort of knowing that the unknown is still out there, patiently waiting as we keep learning how to look. The deep ocean has always been a realm of mystery, a place so vast, dark and ancient that it seems untouched by time. But as our technology improves and our curiosity deepens, the question facing us now is not simply what lies down there, but how should we approach it? The deep sea is not empty space waiting to be filled or conquered. It's a living archive, a place of slow rhythms and fragile balance, and our choices in the coming decades will decide what kind of relationship we build with this final frontier. For most of human history, the deep was protected by its own inaccessibility. The crushing pressure, cold temperatures and darkness made it unreachable. But those barriers are fading. Our submersibles dive deeper, our sensors grow sharper, and our maps grow clearer with every passing year. We can now send robotic explorers to the deepest trenches and recover samples from places once thought beyond reach. Yet this progress comes with responsibility. The ocean is not a blank page. It is a living system, already full of stories. The first challenge of deep-sea stewardship is disturbance. Every expedition, mining proposal or cable route leaves a trace. The deep's calm disguises how delicately it is built. Sediment settles slowly, sometimes over centuries, and a single track left by machinery can remain visible for decades. Coral forests that took thousands of years to grow can be shattered in seconds by trawling nets. Even the smallest particles stirred from the seafloor can drift for kilometers, spreading fine dust that smothers nearby communities. Then there is noise, something we rarely think about, but which fills the deep more every year. Ships, drilling rigs, sonar surveys, and seismic testing all add to the ocean's background hum. In a place where sound is the main channel of communication, even a small increase can matter. Whales depend on low-frequency calls that travel across ocean basins. Fish and invertebrates use vibrations to find food and mates. When our sounds overlap with theirs, confusion replaces clarity. The ocean's ancient soundscape, once made only of wind, waves, and the songs of animals, is slowly being rewritten by engines. Climate change reaches the deep too, though we often imagine it as a surface problem. The oceans absorb most of the excess heat from the atmosphere, and over time that warmth filters downward. Even a fraction of a degree can alter how water layers mix, how oxygen spreads, and how nutrients circulate. Deep currents, the conveyor belts that move heat and carbon around the planet, are shifting in subtle ways. In some regions, oxygen levels are dropping. In others, acidity is increasing. These changes are invisible to us, but not to the creatures that depend on delicate chemical balances to survive. The deep sea is also one of the planet's largest carbon stores, locking away organic matter that falls from the surface. It's part of Earth's long-term climate memory, regulating how much carbon remains in the atmosphere. Disturbing that balance, whether through mining or large-scale extraction, could release carbon that's been buried for millennia. Each layer of sediment is not just mud, it's a record of stability, written slowly by time. Still, curiosity remains our defining trait, and it would be wrong to say we should leave the deep entirely alone. Exploration is not exploitation. The act of observing, of learning, of understanding how the deep functions can help protect it. The key is to balance learning with leaving space for quiet. Scientists already take great care to minimize disturbance, collecting samples sparingly, switching to quieter instruments and sharing data so that fewer ships need to make the same journeys. Every year, the ethic of observe gently becomes stronger. Part of that balance is knowing what we don't know, and that list remains long. The deep ocean holds countless unknowns, entire habitats still unseen, species unclassified, and behaviours we've only begun to imagine. Even now, scientists can't accurately estimate the total biomass of deep-sea life. Microbes, for example, exist in numbers so vast they defy comprehension, forming hidden ecosystems in sediments and rocks miles below the surface. Then there are the behaviours we rarely glimpse. How do animals navigate a world without light? How do they find mates across the endless distances of the abyss? Some deep-sea species may only meet once in a lifetime, and yet their populations endure. Many creatures drift unseen through their entire existence, never touching a solid surface. Others live symbiotically, entire colonies functioning as single organisms. These patterns hint at forms of life profoundly different from our own. Ways of existing that make the deep less an alien world and more a mirror of life's endless adaptability. Even the habitats we think we understand, vents, trenches, plains, still hide surprises. Each year, new types of ecosystems are discovered. Methane seeps, mineral forests, undersea brine pools, microbial gardens that live entirely off chemical energy. Each discovery expands our sense of what life can mean. And still, there are vast stretches of seafloor where no submersible has ever gone, where we have only rough sonar outlines instead of images. If the deep sea were a library, most of its shelves would still be blank labels waiting for books. There's a poetic humility in that thought. Every new expedition reminds us that the ocean story isn't one we're writing, it's one we're just beginning to read. And like any good library, it asks for quiet. The deep thrives on silence, darkness, and time. Its ecosystems operate on scales so slow that our usual measures of progress don't apply. What looks static to us is merely moving at a pace we haven't learned to feel. In recent years, there's been growing interest in extracting resources from the deep, rare metals from seamounts, nodules from the abyssal plains, methane from frozen hydrates. The arguments often sound familiar: energy, economy, advancement, but the deep is not an infinite storehouse, it's a living system. Once disturbed, its recovery may take centuries or may never come at all. The challenge ahead isn't just technical, it's philosophical. We must decide whether our curiosity can coexist with restraint. The encouraging truth is that awareness is growing. International agreements are beginning to form, and public interest in ocean protection is stronger than ever. Projects like global seafloor mapping, deep-sea observatories, and long-term monitoring networks are helping us understand how the abyss works as a whole system. The more we learn, the more reasons we find to tread lightly. Perhaps the most profound lesson from exploring the deep is that it doesn't need us, but we very much need it. The ocean regulates climate, recycles nutrients, and sustains life far beyond its borders. It's the planet's quiet engine, turning unseen but essential. Protecting it isn't charity, it's self-preservation. And so, the future of the deep may rest not in our ability to dominate it, but in our willingness to listen, to hear the soft hum of a current, the faint crackle of distant vents, the quiet pulse of life in darkness. To recognize that curiosity and care are not opposites, but partners. The deep sea asks us to explore with open eyes and a lighter touch, to replace the old ambition of conquest with the newer art of respect. Even with all we've learned, most of the deep remains untouched. We have mapped less than a quarter of it in detail, and we have seen even less with our own eyes. Beneath the pressure and silence, there are still valleys and forests, ridges and rivers we've never imagined. There are species older than cities, microbes rewriting chemistry, and slow dances of life unfolding in total darkness. To know that this exists, that such mystery still survives in a world so often measured and catalogued, is comforting. It reminds us that not all knowledge must be hurried, not all frontiers must be conquered. Some can remain as they are, patient, waiting, quietly teaching us to wonder. The deep ocean is not empty space, it is a library still being shelved. Every new expedition adds a line to its story, but most of its volumes remain unwritten, resting in darkness. And that's a beautiful thing, a reminder that our planet still holds places where mystery is alive, where curiosity and humility can meet in peace. As long as we care enough to look gently, the deep will keep its secrets, not to withhold them, but to share them slowly, in its own deep, deliberate time. Let the breath fall into an easy rhythm like waves slowing after a long tide. The surface is still far above, but in the mind it returns as a pale ribbon of light, a slow dawn after a long blue night. The ocean releases its hold gently. Pressure loosens into calm. Darkness softens into grey. Sound gathers into a quiet hush. The journey through the deep winds upward, with the steadiness of a rising bubble. Across those hidden miles, the world changed by degrees. Light faded first, then colour, then any sense of horizon. Physics took the lead, reshaping everything that lives in water heavy as stone. Bodies without air spaces, proteins guarded by patient chemistry, eyes that either widen to catch a single photon or close the lids forever and listen instead. Where heat thins into steady cold, the metronome of life slowed and held its time. Where light vanished, living lamps kindled. Brief signals, careful disguises, and soft conversations written in blue. Energy kept its promise even when the sun did not. Chemosynthetic gardens rose at vents and seeps, drawing life from gradients rather than daylight, weaving communities around invisible fires and cold flames. In the still deserts of the abyssal plains, a snow of dust kept its slow covenant with hunger, and the smallest movements stitched the seafloor together grain by grain. Trenches took the mind further still, into pressure great enough to quiet thought, where island worlds of species persisted separately, old and new in the same breath. Between those extremes, coral forests built cathedrals from centuries, and sponges filtered the night with the patience of stone. Life chose many shapes for the same problem. Some grew large to store distance and time. Some became ghosts to spend almost nothing at all. Some drifted as larvae across basins the size of countries, letting currents draw new maps of kinship. Some waited, not for seasons but for decades. The deep wrote evolution as endurance, a manuscript revised in long, careful strokes. Sound became the compass when sight was done. Whales traced the world in echoes, fish felt currents through living wires, and storms and ice spoke in low voices across entire oceans. For those who listened, the sea lay open like a map held to the ear. Humans learned to listen as well, first with single pings, then with fans of sound that sketched mountains no eye had seen. Machines carried the questions downward, spheres of glass and titanium, soft hands on long arms, cameras that turned darkness into memory. Each dive asked politely and left lightly, taking only what could not be learned any other way. The picture of the seafloor sharpened piece by piece. Satellites traced the sway of gravity on the surface and guessed at the shapes beneath. Ships stitched swaths of echo into landscapes. Autonomous craft skimmed close to the ground and revealed textures finer than sand. New ridges appeared, seamounts arose where maps had been empty, and ancient landslides froze in place like gestures in rock. The unknown shrank without vanishing, which is perhaps the most comforting way for mystery to live. Care followed curiosity. Noise, sediment, heat, and haste were named clearly as risks, not to halt discovery but to tune its volume. The deep has its own tempos, and kindness to those tempos is simply good practice. Some places need only a glance every long while, some need a quiet watch from the instruments that do not disturb. All of it benefits from the old rule that good guests leave less than footprints. There is more that remains uncounted than counted. The true weight of microbial life, the private habits of animals that meet only once yet somehow endure. The hidden habitats that wait beyond the edges of maps, but none of that is cause for worry. Not knowing is not a failure, it is a corridor. Each unanswered question sits like a small light at the end of a hall, giving direction rather than doubt. A single sentence might hold the shape of this journey. The deep ocean is a library written in slow water. Now the surface nears. The colour lifts towards silver, and a breeze that cannot be felt can almost be imagined. What has been learned settles without hurry. Light fades, physics reshapes, life adapts, and curiosity persists. The ocean remains itself through all of it, not empty, not unkind, only immense. It keeps time for the planet, stores its breath, and turns over its memories with the patience of centuries. Above, coasts and cities rest. Below, the old engine hums. If sleep comes soon, let it arrive like a tide returning to slack water. Let thoughts drift the way plankton drift, unhurried and unafraid. Somewhere far beneath any bed or shore a slow snow is falling. A coral branch adds the slightest ring. A whale's last gift is feeding a meadow of worms. A tiny spark of blue answers another, in the dark. The world is quieter than it seems and more alive than it looks. Sleep well, the ocean will keep its watch.